There we go. All right. So we finished last time talking about formal assumptions of ANOVA, talked about homogeneity of variance. This is the same assumption that we had with our independent sample t-test. We're just extending this to multiple means, right? And discussed how we can think about this as homogeneity of variance across populations, in that we're assuming that whatever we're measuring, the variance in the population variance is equal across our different groups. We can also think about this as homogeneity of error variance. This is going to start to get into some regression-based stuff. Again, if in my model, the only thing that's impacting my outcome is population or whatever my grouping factor is, what should everybody's score in that group be? Should all be the same, right? So any deviation we have from the within group mean is by definition error. It's variability, it's variance that's not accounted for by something in our model, right? So we can think about any type of variance within the population as error variance, right? Due to things that are variability in our scores that are due to something outside of just like whatever group you belong to, okay? And if we haven't modeled that, anything that we don't explicitly model is by definition error, right? So thinking about this, you just kind of think about this in a couple of different ways. Talked about, so if we violate homogeneity of variance, we talk about heteroscedastic errors, things along those lines, fun statistical terms. We assume normality in the distribution of sample means. Again, same thing as our t-tests, right? Do we have specific assumptions about the actual distribution of the data that we're looking at? No, we don't. What we're assuming is that the distribution of sample means is normal. Distribution of sample means becomes normal when either we have reasonably sized cells or whatever it is we're measuring has a normal distribution in the population. And so even when we're going through and doing some screening, even if our data look kind of funky and not perfectly, wonderfully normal, that's all right, so long as we've got reasonable cell sizes, right? Or we want to make sure that we don't have scores that are going to be dragging our means around and stuff like that. But we talk about independence, right? Want to make sure that everybody's scores within and across groups are independent of one another, making sure that's taken care of. And then making sure that our data don't have extreme values that are going to start to mess with our mean estimate. And we want to have sample size that's relatively equal across groups in theory, best case scenario. So again, talking about like, when do we see, so those are our assumptions, but when is our test robust to our assumptions or robust to violations of this? Again, our means-based test, we typically think about our means-based test as fairly robust. They do an okay job. Now there's not 100% consistent agreement in this, but in general, our means-based tests do okay. Violations of homogeneity of variance. These aren't going to be problematic, assuming I have distributions of similar shape. And then also the largest ratio of the smallest or largest of variance isn't around that 4-to-1, that 4-to-1 ratio. Okay. So I can have variances that differ, but really what I'm looking at is sort of within this one-way ANOVA, the ratio of my largest variance to my smallest variance. If it's less than a 4-to-1 ratio, so long as I have relatively equal samples, it's not too bad, right? So we've got a lot of flexibility within this situation. So again, but similar to our t-test, right? Because t-test is just a special case of ANOVA. So all the problems or the concerns that we had in that Bauno article that I asked you about in the midterm, right? What happens where we start to become concerned about the validity of our tests when we start doubling down on violations, right? So if I have any violation of independence, right? This is a methods issue, but if I'm looking at, and again, kind of the classic example of this is if I'm working in schools and I'm looking at, let's say, math scores, and I'm just sampling kids from like 3rd grade classrooms, all the third grade students who are in one classroom, their math scores are probably not going to be independent of one another because they have a common teacher. So any two scores within that class are probably going to be more similar than any two randomly selected scores from across classes. This would be a situation where we've got a violation of independence. And so we would need to use some more complex models to address that, right? But with our standard experimental studies where we're going through and randomizing people, or if we're doing stuff where we're just bringing people in, so long as Allison's score isn't impacted by Haley's score, isn't impacted by Jalen's score, we're doing pretty good. Okay, so this is a methods issue. But in terms of the data, the stuff that we can look at, what we want to look at is if we have different shapes and unequal variances, right? If I've got skew going in the opposite direction and one a lot more variability in one group than the other group, then we start to become concerned, right? If we've got unequal variances and unequal sample sizes, we talked about that, right? The bigger sample is going to have more of an influence on our overall estimate of variability, right? So if my bigger sample has more variability, that's going to make my standard error larger, which is going to make my tested scores decrease. If the larger sample has less variability, that's going to attenuate my standard errors. It's going to inflate my test scores. So thinking about the consequences there. And then violations of normality and small sample size. If I've got really weird skewed distributions and I don't have that many people in that cell, again, the assumption is on the distribution of sample means, but if I don't have large cells, it's going to take a while for that distribution of sample means to reach normality. So we've probably got some issues here. Okay, so these are the types of things that we're going to be looking at when we're going through and screening our data to try and sort of flag like where might I have problems. Okay, now if we go through and we have unequal variances and unequal samples, what we have is an alternative, which would call which is known as Welch procedure. Welch test provides a correction to our F statistic and corresponding degrees of freedom, right? To try and adjust for unequal samples and unequal variances. Thing to remember is just because we have corrected tests and tests that help address this a little bit, doesn't mean that it fixes this issue in our data. It doesn't mean it goes away. It doesn't mean it's not a problem, right? So anytime we go through and take a look at our data and we've got weird stuff going on, that should automatically trigger us to start thinking about like what's going on in our data. Like what's going on with this group where I'm getting a lot more variability or different distribution of scores than this other group, right? This shouldn't be just like a check mark thing and be like, oh yeah, no, it's different. So I'm just going to go through this. If we're thinking carefully and doing good science, we should be thinking about like what's going on, because there's probably something interesting about the phenomenon that I'm measuring that's driving some of those differences. That's going to give you some insight into the behaviors you're trying to capture and understand. Okay. So again, anything that's going into violations of homogeneity, it should be homogeneity, isn't it? Thinking about like what might be going on within these data. All right.
Sorry, Josh.
Yeah.
I should say homogeneity instead of
Heterogeneity. Like I said, violation of, not a violation of heterogeneity, violation of homogeneity, right? Yeah.
On the red.
Yeah. So yeah, just right there, because I can't.
Is it the one above it too, where it says make heterogeneity
No,
go away?
it doesn't. What's correct? It doesn't make sort of heterogeneous variances go away. It's just so yeah. I just that last one. Matt, can you send me an email and ask me to change that slide? It's the last one on this part one. Thank you. All right. So what we're going to do is jump right into actually working with some data. So for this example, and again, I can't sort of reiterate this enough. Anytime we're going through and working with these examples and these setups, always go through and make sure that you understand what's going on, what's being asked, and things along those lines. This is going to save you so much time down the road as opposed to just jumping right into things, right? So have a good understanding of the research question, what's going on, and this will be helpful. So here, with this example, we're saying that given evidence of greater differences in responding to similar versus dissimilar targets. Investigators interested in the extent to which individuals from different racial ethnic backgrounds vary in their response to emotion primes featuring homogenous actors, right? So if you do any type of affect types of research or things like that, oftentimes what you'll have is standardized stimuli that are presented to go through and elicit emotions in people. But what we're doing is we're going to go through and we're going to say, well, cool, but maybe we might see some differences in how responsive people are depending on who the type of people that are portrayed in the stimuli. So what we know is, so we're saying that there's evidence that people tend to sort of affiliate or recognize or connect more with people who look like them. And so maybe just using the standard affect stimulation stimuli, maybe we need to start thinking about who's portrayed in these and who are we trying to elicit emotion from, and sort of wondering if we're seeing differences here. Okay, so what we do is we have a diverse sample of undergraduates, and we're asking them to provide ratings of emotional valence, so very unpleasant to pleasant, and emotional arousal, calm to excited, in response to a humor eliciting film featuring white non-Hispanic actors. Okay, so what we're saying is, like, do we get background differences in how reactive people are to this video that we're showing people? So again, null hypothesis or hypothesis tests or statement of the null hypotheses in statistical notation, running our test, effect size, S value, base factor, and summarize things together. So this is kind of the same thing we've been doing the whole time. Okay, but what we want to do here is start out with some screening stuff. So what I want you to do, pull up your one-way ANOVA set.
And not the post hoc.
Not the post hoc, just the one-way ANOVA. And so we're going to be working from our one-way ANOVA screening handout, which will have everything we're doing here. So if I can find it. All right, so what we've got in this, just 4 variables. We've got our ID variable, we've got our race ethnicity variable here, valence and arousal rating 0 to 8 scale. Okay, so what I'm going to do first is so again, remember that what we're looking at here is when I'm going through and looking at distributions of scores. Can I just look at the whole sample all together all at once? No, Olivia, why not?
Because you need to see if there's differences in everything, kind of like.
Yeah. Conceptually, I'm working with different populations, right? So I can't just lump them all together. I mean, I can, but for the screening, if I've got 3 different groups here, right? What I want to do is look at distribution of scores within each one of those groups, right? So I'm gonna do a quick check here to see on my ethnicity variable, and then this is just my right click and sort, not missing anything. I've got 0, 1, 2, all that looks good. Valence is 0 to 8. Those all look good. Arousal. Those all look good, right? So no missing data or anything that I need to go through and take account of sort of right away. So what I'm going to do is I'm going to go to data. Excuse me. Data down to split file. And I'm going to compare groups, and I'm going to go through and organize output by groups. And I'm going to go through and group people by my ethnicity variable here. Okay. Or compare groups. There we go. All right. And then I'm going to go through and paste that. All right. This here is not any different than anything we did for our independent sample T screening. Same stuff. We've just got more groups to deal with. Okay. So I'm gonna do that, and then I'm gonna go analyze, I'm gonna go descriptives. I'm gonna look at my valence and arousal ratings, right? Drop those over. I say save standardized values as variables, because that's gonna create my z-scores. And I'm gonna go options, I'm gonna request skew kurtosis values, continue there, and then paste. Okay. So if I go through, run this, I'm gonna split everybody up. And I'm gonna get some output here, but I'm gonna throw up the PDF just because it's gonna be a little bit bigger. So we can kind of see what's happening. All right. So across our groups here, Haley, what are you seeing in terms of our different groups here?
Looks like number and the samples are pretty varied, like in each, like definitely more predominantly white or non-Hispanic participants. Like four or yeah, valence pretty high. What was it? It was to 8.
Yep.
Okay, so scoring higher on valence versus like arousal mean wise,
Okay.
intensity wise, skewness and kurtosis look fine.
Okay. Yeah, so not too much going on here, right? If we go through and we take a look, we see probably the biggest thing going on here is recognize that we have some unequal groups. Our white non-Hispanic, our black non-Hispanic groups are fairly similar, right? But we've got about half the number of people of our specific other group relative to our white non-Hispanic group, and sort of about the same there. So we've got a smaller group and two sort of roughly similar groups. So already going to be thinking about, okay, so we got maybe some samples that aren't sort of 100% equal. We go down to take a look at our min and our max. Remember, our scale here is 0 to 8, so it looks like everything's in bounds, right? Yeah.
0 to 9.
What's that?
I said on the example slide, it says it's 0 to 9.
0 to 9. Okay, so that's fine. We're still within bounds, right? So we don't have anything falling outside of bounds. So maybe, yeah, people might not have hit like sort of the very top of the mark. I think it was actually an 8-point scale at the top of it. It's a 9-point scale. 0 to 8 is 9 points.
Oh,
You got it.
yeah, because 0 is.
0. Yeah, 0
Yeah.
counts. Yeah.
That makes sense.
Okay. So we're all within bounds. We're good. Skewness looks fine. Nothing sort of really sort of concerning there. Kurtosis, we've got our valence. We got kind of a peaked distribution for our white non-Hispanic group, but probably not anything that's going to be too concerning. Just in terms of just benchmarks, how are we feeling about our cell sizes here? Fine-ish, right? 20 is not huge. 20 is kind of small. 40 for an experimental sort of group, that's a decent cell size, right? So doing okay. It's not, they're not massive, but they're not super small like some of the stuff that we've seen in the past, right? Okay. So what I'm going to do now is I'm going to go through and want to go through and take a look at my distributions here. Okay. So what I'm going to do is I'm going to go through and I'm going to sort this to take my split file off. Okay. And then I'm going to go to analyze, descriptives, explore. And I'm going to say I want to look at valence and arousal. Oops. Put those into my DVs. My factor list is going to be ethnicity. Want to label cases by participant number, right? That's going to, for my box plot, it's going to drop things in. And again, what I'm doing is making sure that I went through and sorted this file to take the split file off, because otherwise it's going to split file and it's trying to split file and then split the thing by ethnicity, and it's going to give me an error message or something looks funky. So in terms of plots, we're gonna ask for our histogram. Go through and continue, and then hit paste, okay? So if I go through and I run this. Again, it's gonna give me a lot of cool information, but it's stuff that I already sort of got in terms of the things that I already need. What I'm doing, this is just a shortcut for my plots, okay? So here we have our histogram for valence and arousal for our white non-Hispanic participants, okay? Johnny, what are you seeing in terms of our histograms here?
Looks like I have maybe a little bit of negative skew.
Okay, maybe a little bit of negative skew. And we can go back up and take a look at our indices. Is there anything that's sort of notable or concerning about any of these?
Lepocatotic.
Yeah, so again, and again, for valence, this was the one where we had some positive kurtosis, right? This kind of that peaked and flat tails. Anything that anybody's kind of noticing up here? Yeah, Mindy?
One to like the far left is like, it's like on an island.
Yeah, we've got someone who's way down here. And if we're thinking about like what we're doing is we're showing someone a funny film, right? And is it doing a good job at what we're trying to get people to do if this is valence, right? Like sort of how unpleasant to pleasant it's doing. Is our film looking like it's at least kind of doing what it's supposed to do? Yeah, for the most part, we got people kind of coming up. We got one person who didn't think it was funny at all. Like someone was like very upset about this, right? Not very, I don't know if they were very upset. They just weren't into it, right? This film, right? And so this is where not that you should know this, but this is, so the film is often used to elicit sort of positive affect amusement from people. Diner scene from When Harry Met Sally. People have seen that movie, right? It's commonly used to go through an illicit sort of amusement from people. But like the clip has like some sexual themes to it and things along those lines, right? And so if I'm looking at this and understanding what I showed people to elicit sort of amusement and sort of how people responded, yeah, I could see someone back, no, I don't think that's funny. I think that's sort of inappropriate or something along those lines, right? Now, are we worried about this person? No, right? They're separated from the rest of the distribution, but they're not far enough down to really start sort of dragging this down. Would I get rid of that person? No, because not everybody's going to think the thing's funny, right? We're just starting to think about like how people are responding to the stimuli that we're providing, and trying to get a sense outside of just like, is this problematic or not? Getting an understanding of what's happening in our data. Okay, so this is looking okay for the most part, right? Pretty good. And oh, whoops. So this is valence for our white non-Hispanic folks, our valence for our black non-Hispanic folks. So nothing too much going on here. And then we've got our non-specific other group. What's going on with this?
Bimodal.
Yeah, it's kind of bimodal, right? And so if I'm looking at this should sort of make me wonder kind of what's going on. Is this a good group?
Other.
No, it's not, right? It's just kind of like, hey, a hodgepodge of everybody else, right? Which is a pretty poor way to go through and run this type of stuff, right? And so recognizing it's a poor way to go through and do things, but still sort of including this in, but this is the type of thing that we might see. I don't know, there's only 20 people in here. Am I super confident about a bimodal distribution? Not super, like, who knows? This could be just some idiosyncratic feature of these data, but it's also very possible that what I've done is I've collapsed a couple of unique populations who are responding to this quite differently, right? And so if I'm just going through and taking a look and looking at this like, oh, do I have outliers, or is this a problem for my analyses? Statistically, no. Conceptually, probably, right? And so just wanting to sort of really emphasize that we're not just doing this to do this. What we're trying to do is hopefully glean something about what we've done, what we're actually asking people to do, to then sort of inform sort of thoughts, criticisms, about sort of our results and what we can and can't, infer. Okay, but yeah, that for sure looks to me like some sort of bimodal distribution, which depending on who I collapsed into my non-specific other group, that could be kind of a big deal, right? To the point where it kind of makes it not a terribly interpretable, but we'll ignore that for right now. Or not ignore it, we'll acknowledge it, but continue on. So here's our box plot. Box plot's not looking too bad, right? We're seeing again min and max across all of these, as indicated by the top and bottom whisker. Median for our white non-Hispanic, our black non-Hispanic groups is almost identical. Median for our other group looks to be quite a bit higher, right? And sort of maybe looks like a little bit of skew based on that, on where that median falls on that interquartile range there, but nothing looking too bad in terms of, from a statistical standpoint, sort of concerns about our distribution. Okay. For arousal, well, that's looking pretty slick, right? I like that. Maybe a bimodal thing going on with in our black non-Hispanic group, right? And then kind of I don't know, we only got 20 people in there, not too much going on, but nothing too sort of concerning going on with this piece of things. Now, if I go through and I take it, now we've got a little bit of difference in my box and whisker plots here, right? Again, whiskers for my black non-Hispanic and my other group sort of hitting min and max, right? So not too concerned about that. But for my white non-Hispanic group, someone tell me what's going on with this. Allison, what's happening with that group there, at least in terms of our box and whisker plot?
There are some data points that are outside of the what's it called?
1.5 times the
Yeah.
interquartile range, right? Okay. What's going on with the interquartile range there, Allison?
It looks pretty small, like things are kind of like clumped in the middle, more so like than the others.
Yeah, what's my median value here?
What?
What's my third quartile, right? We got not a whole lot of variability in this, right? Which is kind of interesting, right? It's saying that for this group, and just kind of eyeballing it, for my white non-Hispanic group, in terms of like how emotionally activated this is getting me, I'm not getting a ton of variability there, right? And if I am, it's starting to fall sort of kind of out there. It's sort of well within the bounds of sort of everybody else, but we've got much less variability. It looks like we've got less variability going on in this group, right? And if I have less variability going on in response to some sort of stimuli, what is that telling me? Just more consistent, right? If we're thinking about anything that deviates from the mean, now these are median values, but if we're thinking about deviations from my group mean as error, do I have much error in this group? No, much more error in this group. I got more variability here. Like folks in my black non-Hispanic group have quite a range of sort of in terms of emotional arousal, how they're responding to this. Much less so for my white non-Hispanic groups, which is kind of consistent with my hypothesis that maybe this stimuli that I'm using is working differently for different groups, right? So kind of an interesting sort of hypothesis. Again, for the purpose of screening, we're mostly just sort of wanting to make sure that we violated assumptions. But what we can do through this process is start to sort of develop hypotheses about things that might be going on in our data, okay? All right, so we're feeling good about that. Nothing too much going on there. So what I'm going to go through and do now is I'm going to go and I'm actually going to just hijack some stuff here. I'm going to take my descriptives. Split file statement. I'm going to resplit by ethnicity, but this time what I want to do is I'm going to look at Z valence and Z arousal, which is going to be my Z scores, my within group Z scores, right? And then I'm going to ask for that. I'm going to get rid of that save command because I don't need to save Z scores on Z scores. I don't need skew and kurtosis for my Z scores because what am I Skew and kurtosis for my Z-scores are gonna be identical to what? Skew and kurtosis, my raw scores, right? That's not gonna change at all. So I'm just going through and modifying this syntax a little bit, and then I'm gonna go through and run this. And this is now gonna give me my standardized scores within each group, okay? So if I go through and I look at this, any huge concerns about from my in my white non-Hispanic group in terms of where we're at with stuff? What do you think, Mandy?
Wait, ask the question again?
Yeah, so in terms of so look at my Z-scores. Anything of note that I might want to take note of here?
It looks pretty decent. Well, the mean is 0 as well as its standard deviation.
Yeah. And that's a good check. If I've done this correctly, what do these scores need to be? What do my mean and standard deviations need to be?
0.
Exactly 0 and 1. If they're not, what it probably means is you went through and calculated Z scores before you split the file. And so you're gonna get, so this is a nice check to go through and make sure that you've done stuff. But in terms of extreme values, Manny, do we have concerns about my white non-Hispanic group?
Wait, not Hispanic? No.
Not really, right? I've got something that's sort of getting close to what we would associate with a P less than point or P equal 0.001, 3.29. Remember, and again, with this is valence, this is the person who didn't think that our video was very funny. They didn't respond to that. That's that person who's hanging out down there. But someone who's probably not going to go through and sort of be too big of an issue, right? How about our black non-Hispanic group, Andy?
Pretty good.
Pretty good, looking all right, nothing too problematic there. My other group,
Okay-ish.
yeah, nothing too bad going on there as well, right? So feeling okay about this. So again, by the time we get to looking at these Z-scores, there's nothing's gonna like come out of left field and surprise you because we've already looked at the distributions and things like that. This is just giving objective numbers that I can go through and tell you, like, this is, you know, so if I were to just say from that valence, the white non-Hispanic valence group, I got a low score, someone setting outside the rest of the distribution. But if you just tell me that, I don't know like how far that is. But if you tell me, oh, it's a sort of Z-score of equal to this, like, okay, now I've got a decent sense for sort of how far out that's landing, right? So all of this kind of goes down. And so again, it's the same thing you were doing for your independent sample t-test. And again, 100% like you need to use sort of this format for your screenings. We got a little bit of deviation in set 4. Make sure that you're sort of using this, structuring your write-ups so that the pattern's onto here. Missing data, nothing. Accuracy, plausibility, we're fine here. We got complete set, 99 scores. Our distributions for our white non-Hispanic group, acceptable skew, prevalence, acceptable skew, prevalence and arousal, some positive for kurtosis, right? We got a value of above 3 for valence, so we at least want to just note that, right? Descriptions of my histogram and my box plot, just kind of going through. This is my way of having you go through and sort of just visually describe what's going on in these in these data. Same thing with my black non-Hispanic participants and my other participants here. Extreme values, I've got a low value for case number 68. No extreme values for ratings of arousal, right? This isn't, and when we're talking about extreme values, right? Like what I don't want you to use hard and fast rules. Oh, it's nothing above this. You got someone who's hanging out down there at the bottom that it's probably at least worth mentioning. Does this negative 3.26, does that sort of cross our threshold for something that's concerning? No, but it's an interesting case. It's probably worth noting, right? So going through and using your judgment there. Black non-Hispanic group folks, nothing in terms of outlying values. Same thing with our other group. Homogeneity of variance, what we're going to go through is we're going to go through and look at that in our ANOVA. what we're gonna see is that we don't have too much evidence for violations for my valence group. But we do have some stuff in our arousal. We kind of saw that already in that box plot, right? Not much sort of variability going on with my one group relative to my others. And so what we do is we go through and we do see that we have a violation of homogeneity variance. So we would say that we have heteroscedastic error in this model. Yeah.
Those p-values are from the ANOVA, or are they?
No, they're from the Levine's test that we'll run when we.
That we will be running, okay.
Run, yeah, no, but yeah.
It's like, I don't have those.
Nope, yeah, those will come when we actually run the test.
Okay.
So recommendations, and again, want you to be thinking about this in terms of you're a consultant. Like someone has asked you, a client has asked you to go through and say, hey, what's going on with these data? This is what I want to do. What's up with this? This is kind of you just kind of outlining like, hey, here's what's happening. We've got an unbalanced design. We've got a modest cell size for my other group. Got evidence for a low rating of valence, my white non-Hispanic group. Just like heads up, not everybody thinks your video is funny. Likely violation of homogeneity of variance, right? So then kind of going through and talking about the sample's unbalanced, highest ratio, just kind of said to what extent is this unbalanced? So my biggest group 41 to 20, right? With the limited number of people in my other category, suggests possible violation of the homogeneity of variance for ratings of emotional arousal. My group with the highest, but so really again, sort of going through and couching this, saying group with the highest variability, or my highest variance is going to be my black non-Hispanic group, and the lowest is my white non-Hispanic group, are relatively similar in size, which might help balance this out, right? So again, wanting to think carefully about, just because I have a violation doesn't mean that it's necessarily a problematic violation. If I go through and look at my variances, my most variable and my least variable group in this analysis are my two groups that are of similar size. So I'm maybe less concerned about this than if it was my other group that had the lowest amount of variability and the largest group had the highest amount of variability, right? So again, thinking about not only do I have a violation, but what are the potential consequences here? The specific nature of that violation might make me be a little bit more comfortable in terms of like, maybe this might not be the worst, right? So then say one student identifying as white non-Hispanic, reported an inordinately low score for valence, right? So we might want to go through and check that, just to go through like, is that an actual score? Did someone miskey something, right? However, individual expected to have limited impact on the mean, given the sample size and the range of the scale. Recommending investigators verify accuracy of low valence for that case. Also, you recommend a robust test for the evaluation of group differences, considering possible differences in variability, right? So again, I'm saying, yeah, so you got evidence of violation of homogeneity, violation of homogeneity. Probably want to use particularly for arousal, want to make sure that you're using corrected tests. Probably we're going to use that Welch test. Probably not going to be the worst, but sort of this is just kind of what's going on. Okay? So people kind of see what we're looking for in this. We're just kind of taking all this together and just kind of putting together some sort of narrative, and basically like a recommendation. You kind of seeing where this is coming from and how I'm kind of building this stuff in. Okay, cool. All right. So gone through, screened, spent who knows how many hours working on that. Now we need to go through and actually just run our one-way ANOVA. Okay. This piece of things ends up being pretty fast. I'm just going to go down to compare means. Actually, here I'm going to just sort this just to make sure I don't get something weird. All right, so I'm going to go down to analyze. Compare means one-way ANOVA. And I'm going to say I want to look at valence and arousal ratings. Ethnicity is my factor. I'm going to estimate effect size for my overall tests. And then I'm going to go to options. I'm going to request my descriptive statistics, homogeneity variance test, and my Welch test. And then we can request means plot too, just to have it in there.
Funsies.
What's that?
Funsies.
Just for grins, okay? All right, so we can go ahead and paste. And go through and just run that one there. Okay, so if we go through it. All right, so if we go through and run this, we get our get our descriptive table, right? Nothing new there. We already ran this. Just want to go through. Always good to go through and request this. Just one, because it'll just be closer in your output. It's easier to go through and grab. But then two, just going through and making sure that people you think should be in your analyses are actually in your analysis. So looking all right there. We go down to our homogeneity of variance, homogeneity of variances. And so again, we have this for emotional valence, emotional arousal. Stated as this, SPSS has now started to do this. There are different ways of calculating or testing homogeneity of variance. Just go based on the mean, right? Like there's no reason, I would be hard pressed to imagine a situation in behavioral sciences where we would need to get this far into the weeds and stuff. I know that sounds surprising to you because it probably feels like I just love living in the weeds all the time, but like, so for this, you probably don't need to worry about it too much. So based on this homogeneity of variance test, Mesa, where are we seeing evidence of any possible problems with this? Okay, for valence, right? So we look at my value here. So I don't have so it doesn't look like I have too much evidence against the null hypothesis of equal variances across my populations. What about for arousal? Okay, what's the p-value for my Levine's test here?
0.002.
Yeah, okay. So there we do. I have evidence, it says that these data are not consistent with the null hypotheses of equal variances across my groups, right? So again, when Kate gave you an asked where my p-values are coming from, it's these ones right here, right? So again, looks like I do have a violation of my homogeneity of variance assumption for emotional arousal, but maybe not for valence, okay? And so this is where we have to start thinking about, like, what is my approach? How do I go through and do things? Sample size, equal variances are gonna be probably the new two things that are not equal sample, but at least reasonably balanced cell sizes and homogeneity of variance start to drive a lot of different decisions that we're making across, like, which way do we go? What specific tests do we use and things along those lines, right? So here I have a case where I have different cell sizes and violations of homogeneity of variance, right? So probably between those two, that's going to say, yeah, I need to probably go through and use that Welch's test for things. Okay. Questions about homogeneity of variance, what we're doing there? Yeah.
This might be kind of a dumb question, but why aren't we looking at homogeneity of variance within each like group that we're looking at? Why are we looking across the measure?
Okay, we're gonna, that is actually an excellent question for about this time in the spring. When we start doing mixed factor ANOVA and stuff like that. With this, what we're doing is looking at across. So the difference is the assumption here is variability across populations. But like you said, and so what, Kate, what do we call variability within groups? What is that? That's my error. And this is what we're getting down to in my ANOVA, right? This is where we're going to partial that out. Okay. So if I go down through and I just take a look at my ANOVA table here, Lindsay, what am I seeing in terms of hypothesis testing for emotional valence?
It doesn't look like it's significant.
Yeah. So so this would, we would, fail to reject this, right? So it looks like I do not, based on my data, that my data look to be reasonably not incompatible with the null hypothesis of equal means across groups, right? So does that mean that there's no differences across these groups?
Not enough to be confident that
Yeah.
there is.
Right. Again, I'm not saying that white Hispanic, white non-Hispanic, black non-Hispanic, and sort of my homogeneous other group or my heterogeneous other group, that there's not differences. I'm just saying that we don't have enough data here to suggest that there is, right? So again, an important distinction, and one we always should be keeping in the back of my mind. Like if I say there's no effect, it sounds like that, like, oh, there's nothing going on. And I can just wanting to make sure that we're recognizing that just because we fail to reject doesn't prove them. Okay. What about Lindsay, emotional arousal?
So similarly, there's like we're not confident that there's a difference.
Yeah, right. Because it's that 058, right? And it's sort of right on that thing. If that was 0.049, is that a categorically different response? No, right? But it's kind of right in there in that sort of weird. I mean, I could try in a publication to make an argument for it. Some people might be fine with it. Some people might sort of get mad at me about trying to do that, right? But if we're doing sort of our yes, no criteria, that would be a fail to reject. Yeah, Haley.
Do we, so with the violation of like assumption, with the variance, the test of homogeneity variance.
Yeah.
Since we violated that assumption, can we, in terms of interpreting then arousal with the ANOVA?
Yeah.
Does that,
And you're sort of just a step ahead of me
okay.
because we did have that violation. We would say we're not confident in this, right? And so what we would go through and use our corrected test. So wanting to call attention to see kind of what that p-value was before we move on to the next thing, right? And so, but again, it's kind of in that ambiguous thing. Like we would say, and you would probably have to make a strong argument to sort of make an interpretation of this just based on where it's at in terms of the omnibus test. But in our minds and in our hearts, we know that this really isn't that different than if it was just on the other side. Suggest that there might be something there-ish, but I don't know. We had decent cell sizes for a couple different groups, not so good for another group. Even 40 for a cell size for between groups difference it's not terribly powerful. We have to have decent effect sizes that we're going down through and taking a look, but it's all kind of ambiguous here, right? But if we go down through and scroll down to my robust equality of means, this is my Welch test, right? Lindsay, what are we seeing here when I go through and I look at my corrected test?
So when we're looking at emotional valence, it still doesn't look like there's a
Yeah.
difference, but then with arousal, it's like there may be a difference.
Completely different thing, like completely like category wildly different, like it was hidden and now it's found, right? It's not that much different, right? But it's enough to go through like with the more appropriate test, right? Given the violations that we've had, yeah, we do have evidence to sort of make a claim that, yeah, we do have at least some evidence, right? And again, if we're going through and thinking about P as a continuous indicator of evidence against the null hypotheses, it's not strong, right? If we calculate S in Bayes, it's going to be pretty much. So we probably shouldn't be, if we're thinking carefully about this, we probably shouldn't be over the moon and think like, oh, before, like now, but it's like a pass. Right now I can talk about this as evidence for an effect where before I couldn't, so we got to sort of play within the rules of the game that sort of are sort of not of our own construction, but sort of at least kind of knowing the types of things that go in there. Okay. So only last thing we want to take a look at here is your effect sizes. SPSS within the last couple of years has gone through and started to do this, which is nice. We have our eta squared and then our omega squared fixed effect. That's going to correspond to our eta squared and our omega squared that we talked about in the lecture slides. We've got our point estimates, we've got our upper and lower bounds here. Now remember, sort of our eta squared is functionally equivalent to our R squared for like a regression model, right? It's just telling me the proportion of variability in my outcome variable that is attributable to my grouping effect, right? It's just an R squared value, right? But what is our concern with eta squared?
It's the sample, right?
What's that?
It's referring to the sample, not the.
Yeah,
population.
yeah, our eta squared is always gonna be positively biased. It has a particularly strong positive bias, right? Remember, this is a measure of association. Can I have my predictor account for less than 0% of the total variability of my outcome? No, it floors out at 0, right? So, and I'm never gonna get exactly 0. There's always gonna be, even when the null hypothesis is completely true, this value is gonna be like something that's marginally higher than 0, right? And so this is where our positive bias comes in. So with our eta squared, this is a really nice descriptive statistic for what's going on in my sample, right? So if I was going to interpret this, I would say within this sample, it looks like participant background is accounting for about 4.3% of the total variability in valence scores, about 5.8% of the total variability in arousal scores. Okay. But if I want to go through and I want to make a population-based estimate, which is kind of what we're doing, this is where we go down to our omega squared, right? And so if we're talking about eta squared, I'm going to interpret that within the context of these data, within this sample. Here, I would say our population estimate for total variability in arousal ratings that's accounted for by participant background is probably about 3.8% of population variability in arousal or something like that. Just making the distinction between omega squared as a population-based estimate. Omega squared is still positively biased, it's just less biased than eta squared. Eta squared is a nice measure of what's going on in my sample. We'll probably have to be careful about trying to use that as a estimate of some population effect. Okay, people kind of see the difference between those two conceptually.
I just don't remember how omega squared is a population estimate.
It's a corrected statistic, sort of based on output from our ANOVA table. It just kind of shrinks it down a little bit to try and prevent that positive bias.
So we don't have to have any extra information in there about a population. It
No,
just creates
no.
that
It
estimation.
just attenuates it a little bit. Think about it's not the exact same thing, but think about this is the difference between G and unbiased G. Now G is going to be biased in like really small samples, but as samples get decently sized, it's going to be less problematic. Same thing again with eta squared, but eta squared is just a more biased statistic. So omega is just kind of going through and getting this for us. Okay. Now the only thing about omega is omega works great, but it assumes relatively similar, relatively balanced design. We got about a 2-to-1 difference in sort of our smallest to our largest. So we started to get like, so this is one of the things that like sort of, if I have a wildly unbalanced design, probably takes omega squared out of the picture because then I kind of lose stuff right here. Probably okay-ish, but just something that you want to be thinking about in terms of what do I go through and select as an effect size. Yeah.
So when we're reporting the ANOVA effect sizes, do you want us to, would we, unless we have like, like you were just saying, the really unequal sample sizes or whatever that may be, do you want us to go ahead and report the omega squared?
Yeah, omega is a better statistic unless there's something about the design that makes that not tenable.
Okay.
Yeah. Okay. So that is all easy peasy relative to stuff that we have to go through and work on in terms of our screening. Screening is always going to take far more time than actual running your analysis. But if we go through and do that, we learn a lot about our data, and we make sure that we can say actual things with confidence about our analysis, right? So here, just walking through steps, what things look like in ANOVA or in our output from SPSS. Here, this is me just doing old school stuff, calculating effect sizes by hand, just so you can see an application of those formula. Again, SPSS didn't used to do this for us. Now it does. So, but this is just how we would go through and calculate those by hand. So just go back through and take a look and cross-reference that with the formulas provided. Okay. Johnny for Stata. Like Stata doesn't just, SPSS just kind of dumps out a whole bunch of information, whether you want it or not. Stata, you have to ask for it. So here, we're just saying this row bar command is just asking, this is for our Levine's test, ANOVA, valence ethnicity, gives us our ANOVA table, okay? If I ask W test, that gives me my Welch, right? Here's some cool plots Stata will go through and do for you in terms of mean plots, which are kind of nice. Once you go through and enter those things, once you run your ANOVA, E stat, E size will give you eta squared, E stat, E size omega will give you omega squared, right? So just different ways to go through and do that stuff. Yeah.
So sorry, I meant to ask this,
Yeah.
for when we were looking at the output, the robust test of equality, like of means, do we use that? So that's pretty much like a correction,
Yeah.
right? So if we violate the, like homogeneity, the variance, if we violate that, then would we refer to that statistic? Okay, but if we don't violate it, we're referring to
Yeah,
the,
then we're good. Yep.
okay.
And the question is like, and I've had this question, if I violate homogeneity of variance, then what do I have to make a correction on my effect size? Because the effect sizes come from a different thing. Don't worry about that. It's just a ratio. It is what it is, right? And sort of going through and report back these things. All right. So how do we go through and write this up, right? So we're up here talking about, again, this is just for these examples, it's kind of nice to just kind of tie this together. This is what I'm sort of going through and looking like, reminding myself of what we're trying to do with these analyses just to begin with, right? And so here we go through into what we might write up in terms of a thoughtful analysis of or summary of what we've done. So we've got evaluation of responses for emotional valence, relatively compatible with null hypotheses of similar scores across groups from different backgrounds, right? There's nothing much to say there. It's just like we didn't find evidence for it, so just kind of drop everything in there and kind of leave that. There's nothing here that would sort of lead me to sort of need to elaborate more, right? Some like as if with our t-test, right? I have a massive effect size, but I fail to reject the null. That might warrant a little more commentary to say like, well, it's probably a small effect size or a small sample size. It's underpowered. I want to just kind of go through and look a little bit more at this. With this situation, there's not much. I don't know. It just looks pretty similar in terms of things, right? But we say a Welch test for ratings of emotional arousal, by contrast, demonstrates some evidence possible differences across white non-Hispanic, black non-Hispanic, and heterogeneous other groups, right? So then we got our Welch test, our P, or omega, S and B base factor, right? Our estimates of omega squared, which gets approximately 3.8 of the population variability in ratings of arousal, but can be attributed to racial ethnic differences across viewers, right? So again, seeing I kind of worked in that population-based estimate there, so to let you know that I'm going to talk about population-based stuff, right? Following correction for unequal variances base factor indicates odds of different responding across racial groups are at most 200% more likely than the odds of equal ratings across, right? This is just working in base factor, sort of like alternative odds of the alternative relative to the odds of the null. And here we're saying, whereas data are limited by modest samples and the inclusion of a heterogeneous other group, results offer preliminary support for differences in some difference affective responded to standardized film, right? So again, making the note here that this other group is problematic because I don't know who's in that other group, and having sort of a comparison just other group really kind of limits what I can say about things. But what's going to happen is overall, with this overall ANOVA, with this omnibus test, does this tell me where differences are at or what's happening or where my differences are occurring? No, right? In general, based on this, we can say it looks like background does maybe have a difference in terms of certain aspects of how people are responding to this standardized film. Well, standardized to who, right? We need to take that into consideration. And so it does look like it has an effect, but do we know what the nature of that effect is, kind of who might have differences, things along those lines, based on our omnibus test? No, it's just saying that there's a difference in there somewhere, right? What we now need to do is go back through and start to tease this apart and figure out where those differences are. Okay. Questions on the overall ANOVA model, sort of going through this. Feeling all right? Yeah, man.
I have a question about, the last population of other.
Yeah,
Wondering, like, is that like a mistake that like the researcher made where they did not have an identity, like an ethnic identity
Yeah.
for them, or
Well, I mean,
they
this,
can't report it?
so this is like, I mean, this is an example based on some of my dissertation data that I collected down at the University of Memphis, where the breakdown of white students and black students about relatively equal, and then a smaller sort of portion of people identifying as Hispanic and Asian and sort of other groups, right? So this was not an analysis. This is something that I've constructed for the purpose of this group, but you see this all the time, right? Is that we've got like, okay, here's white non-Hispanic or our other group, when that other group is now functionally meaningless, right? Or here's these groups, and then we've got sort of the other group that's kind of a hodgepodge of other people, right? And so that is our way to do things, right? But so the consequences are like, can we say anything meaningful about that sort of group if that's where our differences lie, right? And so this is where we need to go through and start running our follow-up tests to see, okay, we've got an omnibus effect that says, yeah, background looks like it might have an impact on how people respond to this experimental stimuli. What we need to do now is go through and try and see kind of where that's coming from. Does that help?
Yes.
Okay, so yeah, good question. This isn't just people who like did not identify on the demographics group. It's just people who didn't identify as white non-Hispanic or black non-Hispanic. Other questions? All right, cool. So our omnibus app tells us, gives us evidence that, or what we're inferring is at least one population from which individuals were sampled is different from the rest, right? So there's something going on in here somewhere, right? But in order to determine where those differences are occurring, we have to do some follow-up tests with our ANOVA, right? And so our classic approach to doing this says what we need to do is we need to go through, we first need to do our omnibus test. And then once we got our omnibus test, if we have evidence for differences somewhere in these groups, what we can then go through is then do sort of starting to piece things apart and make specific comparisons. When my overall, when my alternative is not supported though, when I fatally reject the null hypotheses, the argument would be that it's now questionable to proceed in terms of running follow-up tests, because now we're just like trying to pick up sort of random stuff that would have come up, right? So again, the classic approach says it's kind of a stop-go thing. If I don't find evidence for an omnibus effect, I should not be moving forward to start playing around, teasing it apart, looking sort of this group versus that group. Okay, but Powell and other people make strong arguments against sort of this approach and the utility of our omnibus test at all, right? Arguments here that my F test starts to become sort of attenuated if I have one mean that's different, but everything else is kind of all the same, right? If I have, let's say I have 4 groups, right? And maybe I don't have a real big cell sizes, and group 1, group 2, and group 3 are all pretty much the same. And then group 4 is kind of a little bit different. The similarities across those 3 groups is kind of going to swamp out sort of that other group that might have meaningfully differences, but like sort of the overall ANOVA, particularly as these ANOVAs get quite large, the more groups you have in there, the concern is maybe we swamp out important differences, right? With the way things are set up. Other argument is that the inclusion of our the omnibus test and our type 1 error is going to provide too conservative a follow-up, right? So again, remember that with compounding error, right? Each one of our tests, every comparison we make is conducted at an alpha equal 0.05 level. But if I do 20 of those, my cumulative type 1 error, the likelihood of me making at least one type 1 error within this set of things now goes up. And if I go through and I throw in an omnibus test, it just tells me that something's different than something. I've added a test in there that increases my cumulative alpha, but doesn't actually get me that much closer to what I actually want to go through and test, right? And so some problems there. And Howe also argues that this omnibus test is something that we do by tradition, but it's not really anything that people are overly interested in for the most part. This idea that that I'm gonna go through, run this omnibus ANOVA. And then I'm just going, okay, so I had a significant ANOVA case closed. No, you're always gonna have to go through and do more stuff here, right? And so if we're going through and thinking about the benefits of our ANOVA model that we talked about before, more efficient than multiple t-tests, well, kind of. But even if I do get a positive test, I'm still gonna have to go through and do follow-ups anyway, so maybe not as much as we would have thought. Avoids complications with type 2 error, well, kind of, but if I have to go through and run those comparisons anyway, those individual pairwise comparisons anyway, now I've added another omnibus test on, so I've actually increased the number of tests that I'm running. Providing greater flexibility in designing experiments, yes, it is sort of good with that in terms of like, here I've got an experiment, these are the relevant conditions, but diminishing returns in terms of these other two things. And so this, Kate, is where you had asked about before, you know, from certain experimental traditions, the argument would be to, okay, run your study with your 3 or 4 different groups, but then what you should have is very specific hypotheses about how those groups should differ. Who cares about the omnibus test? I don't know. My question isn't whether one group, some groups differ than other groups. The question is these specific contrasts that I'm sort of going through. And so scrap the omnibus test. I don't care what that says. I'm going to go through and test the things that I put the design together to go through and take a look at, which you will get probably pushback from most people, because most people will say, no, you have to go through and look at the omnibus before you can move forward. If I called my shot 7 months ago, and these are the things that are actually important to me, the methodological high ground would be to just test the things that you wanted to test and you did it in the first place, right? So it's a push-pull between method and so what's done by tradition. All right, so managing our type 1 error. What do we go through? How do we go through and address this? Our per, so getting our terminology straight starts to become important. Our per comparison error, this is the probability of committing a type 1 error on any given test. Okay, so for every test we run, we set alpha. Alpha helps us control the likelihood of making a type 1 error, saying that we found an effect when in fact no effect exists, right? And again, we set this as alpha, right? Now my error rate per experiment, this is going to be identified as the expected number of type 1 errors in a set of comparisons, okay? So if I run 5 comparisons, my error rate per experiment says in this experiment where I ran 5 different comparisons, what's the expected number of type 1 errors in that set, okay? We calculate this as the product of your alpha level and the number of comparisons that you put together, right? So if I have 5 comparisons, I have alpha 0.05. So give me what's that number? What's that? Yeah, 0.25, right? Now, be careful because this is number, right? I would expect to have 0.25 errors for this set of comparisons, right? Which is not a full thing, but like if I start going through and sort of increasing the number of tests that I'm running in an experiment, however I want to define that, that starts to increase, right? And this C times A is derived from our Bonferroni inequality, okay? Which says that the probability of occurrence of one or more events can exceed the sum of the individual probabilities, right? So it's saying that, like, if I go through and sort of individual probability of on each one of these events, right? That the probability of the whole thing happening can exceed the sum of these. This is kind of just where this is getting into that Bonferroni correction that we'll talk about a little bit later. Okay.
Is that a shortened word for comparison alpha?
What's that now?
CA?
What's that?
CA, is it for like comparison alpha?
No.
Oh, it's
This is
for
just
that
this is just C times alpha.
one.
It's
Comparison
just
times
yeah.
alpha.
It's just the product of those two values.
So
Yeah.
5 times 0.05,
Yeah.
right? If you've got
Yeah.
5 comparisons.
Yep. All right, and then we got family-wise error. This is the probability, so back to what you were talking about, here, this is the number. Family-wise error is the probability of committing at least one type 1 error across a series of comparisons. Calculate this as 1 minus 1 minus alpha to the C power, right? Which C is your number of comparisons. So here with 4 comparisons, each at alpha 0.05, our family-wise error rate is 0.185, right? So we're getting close to a 20% probability of committing at least one type 1 error across a set of 4 comparisons, right? Which is a lot different than 0.05, right? So we start to see how this compounds from a statistical standpoint. Okay. Family-wise error is going to be bounded by alpha and number of comparisons times your alpha, but we're generally going to assume that sort of this is going to be fairly close. All right, so in terms of thinking about how we go through and approach our follow-up test, this needs to be a very, very thoughtful approach and process. It's going to depend a lot on your research question, your data, the design, what you're trying to do. Okay, there's no like template to go through and be like, oh, this is the right way to do things. There's just a lot of different factors that need to come together and sort of thinking about what's my plan for going through and taking a look at things. You should probably have a plan that's made before you actually even go through and start running the analyses. This is a thought experiment. Like, what do I think is going to be different than what, right? Again, being selective, looking at comparisons that are going to be meaningful, okay? Testing all possible comparisons. If all possible comparisons aren't meaningful or interesting, is going to be a poor approach. Alice, if you're running a one-way ANOVA, you got 5 different groups, right? And you're going to want to go through and test all possible combinations, pairwise combinations of all of those groups. You better be ready to tell me why each one of those comparisons is theoretically meaningful and interesting. Because if you can't, or say like why you would expect a difference between 1 and 3, but not 1 and 4. If you can't give me a good reason for that, this probably means that it's not something to be going through and testing everything, right? What we do is we waste power, because if we're correcting for all possible comparisons, but all possible comparisons aren't interesting or meaningful, I'm correcting for things that are irrelevant to my interests, which is making it harder for me to claim evidence for my stuff, right? Also, if I go through and I compare all possible comparisons, I better be ready to talk about all possible comparisons and explain why the pattern effects emerged the way it did. And if there's like 20 different comparisons, that's a lot for me to talk about, and I probably don't have a good reason for why things come together, because there's no reason to expect differences, but things came up, right? It turns into a mess, right? So thinking about being selective in terms of what we're doing and sort of our approach is always going to be the methodological high road here. Okay. What we want to do is we want to choose a strategy that manages our family-wise error across planned and unplanned comparisons. SPSS will not do this for you. If you tell SPSS to go through and run comparisons, it's going to correct for everything or correct for nothing. What you need to do is be thinking about, like, what are the things that are maybe my a priori hypotheses? What are the things that are important to me? The reason that I'm running this study. And so to say, these are my most important things. And then maybe there's some exploratory stuff, right? Like, well, it would be interesting. I don't really have a reason to think that these would be different, or maybe I do, but it's kind of a hunch, right? Separating maybe your planned comparisons out from your more exploratory types of things. And maybe for your planned test, I'm going to run these as per comparison error rates. My exploratory stuff, I'll go through and just correct for those, just because I'm kind of playing around with the data, seeing what happens. Okay. Have a good reason for examining the comparisons that you're comparing. Right? This is a great quote out of the Howell textbook. The fact that you're able to do something is really sufficient reason for actually doing it. This is just a good life mantra, right? Just because you can doesn't mean you should, or it's a good idea, right? Particularly for this type of thing. If you just go through and get lazy and look at all possible comparisons between all possible things, it starts to become problematic. It's a lot to go through and talk about, right? From our Wilkinson article, Researchers rarely need to compare all possible means to understand their results or assess their theory. By setting sites large, they sacrifice the power to see small. I like this piece. The lattice of all possible pairs is a straitjacket, forcing themselves aware it restricts researchers uninteresting hypotheses and induces them to ignore most fruitful ones. The specific contrast interests you, examine it. If all it interests you, ask yourself why, right? Again, we can do so many things, and it's kind of cool to be able to go through and sort of move beyond our t-test where we just say, does this group different from this group, right? Like, oh, I've got this elaborate design that's got all these sort of different comparisons. Cool. But you better be able to you better be ready to go through and talk about all the random stuff that could pop up all over the place. And if you can't do that, or if it's not interesting to your research question, maybe don't fool around with it, right? I have this battle with the reviewers sometimes, but I go, oh, why didn't you look at X, Y, and Z? I wasn't interested in that. It has nothing to do with the thing that I'm interested in. What it is, I gave you mean standard deviation sample size. If you want to look at it, go nuts. Like, you do it if you want to. It's free country. No one's going to stop you. It's just not relevant to the stuff that I'm doing right now or the story that I'm trying to tell. So I've given you all sort of the tools to go through and fool around with whatever you want. These are the things sort of that I've laid out very explicitly on the front end. This is what I'm interested in. This is how it relates to my theory. This is what I'm going to go through and do. I did that thing. I talked about that. I don't want to talk about all possible things, right? Because then that starts to get boring and redundant with stuff. Okay. So go through for any of your stuff, just make sure before you, and this should be done in the planning phase, right? Thinking about like, what are my specific, why am I doing this in the first place? What are the comparisons that are going to be most meaningful and tell me the most about the thing that I'm trying to study? Lay those out, have a strategy there, and then maybe later on, once you've gone through collected the data, if there's other cool stuff, there's always cool stuff that pops up that we didn't expect. So maybe go through and say, okay, these are some exploratory stuff. We're going to take a different approach with that. Okay. All right, cool. So let's go through, take a break, and let's be back at 3:40. We're gonna jump back in. So.
Mine's just about to die. I just have to leave it. Otherwise, yeah.
I was ready to do that. I was ready to do it with office scissors.
She was like grinding so. Not right now.
Proud of myself. I remember to turn the video on, turn the sound on. That's professional. All right.
Never.
How are we feeling about this stuff?
Don't forget to turn.
Pretty good.
I did.
Okay.
Yeah.
Just making sure.
Thank you. Always double, triple check.
So far, so good.
So far, so good. Feeling okay. So understand. So where our omnibus tests are telling us, and then sort of what we need to go through in terms of follow-ups, correct? Okay. So in terms of thinking about follow-up tests and our strategy for this, wanted to make sure that we're differentiating between a priori and post hoc approaches to testing. A priori comparisons, these are typically going to involve a limited set of theoretically meaningful comparisons chosen before we go through and actually do data collection, right? This is for your thesis. You're saying, I'm going to run a one-way ANOVA with this thing. Here are the specific comparisons across these groups that are going to be most meaningful in terms of telling me something about the phenomena behavior I'm interested in, okay? And what we do is we typically will look at these as a set of linear contrasts or independent sample t-tests, so depending on what the nature of those tests are. And traditionally, what we do is we look at these at per comparison error rates. The idea being is that you called your shot way in advance before we even collected the data. You said the reason I'm doing this study is to look at the differences between this and that. And because of that, we're going to grant you the ability to go through and look at these at per comparison error rates, right? Which is going to improve the power of these tests. Now, some people will make an argument for still making a correction for family-wise error with a couple of different corrections. If you want to take a more conservative approach, certainly you can do that. But the thing I would say is if you're going to do that, make that decision before you collect the test. What happens is sometimes like after I collect the data and I get something that's 0.04. But if I were to correct for it, it wouldn't come up. So then I sort of magically decide that, oh, I'm not gonna go through and do that. Or I go through and look at it and everything, all my tests are coming up 0.00000001. I'm like, okay, I'm gonna bond for ANOVA correct for all this when I already know it doesn't make a difference because everything I wanna test is gonna be fine anyway, right? True a priori, honest a priori stuff, it's happening before you go through and look at the data, right? This is all the stuff that goes on in your thesis proposal type of thing, okay? Post hoc comparisons, often what this ends up being is a comparison of all possible, or an analysis of all possible pairwise comparisons. Typically what we see is I go through, collect the data, run my ANOVA, and then look at where my means are. And then I start thinking about like, oh boy, I wonder if that group's different than that group. I'm interested, I wonder if that group's different than that group, right? Probably what's going on is not that that's driven by conceptual stuff. It's sort of driven by, hey, this mean looks a lot bigger than that mean, right? And so what happens here is what I've done is I've actually in my head gone through and looked at all possible comparisons. And then I'm just selecting the ones that are sort of the biggest to go through and take a look at, kind of cheating, sort of our alpha rate or our error rates go through the roof. And so here, what we go through and we'll typically do if we're going to do that type of approach, it's going to generally involve a set of post hoc comparisons that are comparing all possible comparisons in the set. Easy to obtain in SPSS, but a real pain in the ass to go through and sort through and figure out and describe in any sort of meaningful way, okay? Note that our limited planned a priori contrasts always going to be more theoretically and methodologically defensible, okay? There are a lot of different things you could look at. What you should be thinking about is what's the most meaningful, what's the thing that's going to most directly test the ideas that I have about how these groups should differ, okay? Again, and we're gonna see, like, I'm gonna have you do an analysis, work with some post hoc stuff, and you're really gonna think it's a pain in the ass because there's gonna be a bunch of different tests that you have to down describe and sort of think about reasons why these groups are different when maybe there's not a good route, but you've gone through and done it, and you can't just cherry pick the ones that you like and ignore the ones that you don't like. You got to talk about it all, right? So again, rationale for exploring all pairwise comparisons should be equally, if not more compelling than sort of your arguments for looking at a small limited set. Now, someone will always say, well, why don't you look at this group or that group? Why don't you look at this group or that group? Because that might be relevant to my interests, but if not relevant to your interests, it's not why you set up the rationale for the whole study. You're probably okay to leave those, set those aside, so long as you set up a reasonable rationale for your project. So, for our planned comparisons, again, the idea with planned comparisons is that we get credit, we get a little bit of an edge because we plan these in advance, okay? If I've got a situation where I'm wanting to conduct pairwise tests. We want to talk to my brother.
Just answer it.
What do you want? If we're going through and if our follow-up tests involve specific pairwise comparisons, okay? What we can do within the tradition of ANOVA is we're going to calculate a t-test. And the t-test is going to look like sort of the t-test that we sort of normally go through and use. Only difference is here we're going to take for whatever two groups we're wanting to compare, difference in means over the mean squared error from my ANOVA table divided by the sort of number of people in that cell, mean squared error over this. Someone remind me, what's my mean squared error for my ANOVA table? Johnny?
It's the variability within groups.
Yeah, it's my within group variance, right? We call it mean square. Mean square just means variance. It's in a one-way ANOVA, your mean squared error is just literally the pooled variance across your entire design. It's the pooled variance for all your groups. Okay. And so with if we're looking at pairwise comparisons within the context of ANOVA as a priori follow-up, we're going to calculate our test statistic. We're just going to use the mean squared error. We're going to substitute the mean squared error where we would normally have our pooled variance estimate, and we just drop that in there. Okay, so easy peasy. Okay, but the thing that really gives us the additional power is by tradition, what we would do is then we would set our t critical to be our t statistic for our alpha divided by 2, so whatever, for our two-tailed test. Whew, I ran out of air there. Times our degrees of freedom error. What is this gonna do to our critical value? What's the degrees of freedom error from our ANOVA gonna be relative to the degrees of freedom we would expect for comparing just these two groups? I think, Johnny, I just see you sort of overtly processing things. As the degrees of freedom error for my overall ANOVA going to relate to the degrees of freedom from any two groups within that ANOVA? What's going to give me more degrees of freedom?
Looking at the two groups like separately or like outside of the ANOVA.
Okay, so let's say I've got a one-way ANOVA with 4 groups, 20 people within each group, right? So I've got 20, 40, 60, 80 people in the overall ANOVA, right? And so then for my overall ANOVA, degrees of freedom error for the overall ANOVA is going to be, what is it? 8 minus 3 is that right? 77, something like that. What if I just do, what's my degrees of freedom going to be if I just go through and look at group 1 and group 2, Mesa? 38, right? Degrees of freedom error for my ANOVA is going to be a lot bigger than degrees of freedom error from just the 2. And if I have a lot more degrees of freedom, what does that do to my critical T? Drives it down, which makes it easier to go through and sort of claim evidence for my effect. So what I'm doing here from a traditional follow-up test, what I'm doing with this is I'm capitalizing on the overall design to add power to my test, okay? So between sort of what I've got here, if I've done this correctly, I'm saying that I've got, and again, in the I got 4 levels, my IV, 20 people in each cell. I've got 80 people that I'm using to go through and get an estimate of the error variance across each group. So the variability across each groups. My assumption is that my error variance or my that I have not violated homogeneity of variance, that all these populations have equal variability. And so my estimate of the total variability with 80 people is better than 20 or sort of some subset of that. And so what I'm doing is I'm calculating, I'm banking on a more precise estimate of the population variance, plus the fact that I've got a lot more people in the whole design relative to these 2 groups. And so what ends up happening is I go through and calculate my test statistic based on the mean squared error from the whole design, right? My mean squared error is the pooled variance across all of my groups, and dividing and sort of taking that and comparing that against a critical T that has degrees of freedom from my overall ANOVA table, as opposed to just the 2 groups of question. Yeah.
You said that the degrees of freedom error, as that increases, our critical T increases? Is that
No,
what you said?
critical D decreases. As my degrees of freedom increase, my critical T decreases, right? To the point at infinity where it becomes a Z distribution.
Which you said then in turn increases our chances of.
Increases the power of the test, right?
Okay.
So essentially what I'm doing is I'm running a comparison across 2 groups of 20, but my degrees of freedom are capitalizing on the full 80 people in the full design. And so I'm getting an advantage with this piece of things. Okay. Yep.
I guess I'm just a little confused because with the critical T,
Uh-huh.
what I imagine is if my degrees of freedom error increases, it's gonna increase my critical T.
No, so your degrees of freedom error, you just don't get tripped up by this error thing. I mean, this is the degrees of freedom error is the sort of the cell that you're pulling from your overall ANOVA table, right? But anytime the degrees of freedom, my degrees of freedom go up, what happens to my critical value? It goes down, right? So I'm just plugging in a bigger number here than I would if I was just running an independent sample t-test,
Okay,
right?
okay.
So basically I'm essentially you can think about this as I'm kind of running a version of an independent sample t-test with 40 people, but I'm pretending like it's sort of, I'm banking on the overall design that has 80 people. So I'm basically, for the purposes of this test, I'm functionally doubling my sample size.
Cheating.
Yeah, we would say that it's not cheating. What we would say is we're banking and capitalizing on the fact that you put together a really nice, well-balanced design where we don't have violations of homogeneity, things along those lines. And so what we're doing is we're sort of capitalizing on that, right?
So if there are violations though, oh.
If there are violations, right? If I have unequal cells or unequal variances, what we can then do is just fall back on our regular old t-test, right? This is gonna be the more conservative approach, but it's gonna be a pretty robust approach, right? And so this is why it starts to become important. And when we're doing our screening, kind of understanding, do we have violations of homogeneity of variance? Do we have differences in sample sizes? Have I set this up in a way that is gonna allow me to capitalize on follow-up tests by using some of this traditional approach, or am I gonna have to probably scrap it and just fall back on just running t-tests and things like that? Okay. So again, within the context of experimental research, which is where kind of all this sort of developed, right? If I have, I'm bringing people in, I'm randomizing them to condition, everything's pretty much even Steven. It's a nice tight controlled experiment. This type of stuff works pretty well. If I'm a clinical person and I've got people with depression and who I have partial depression and people who don't have any depression, I'm going to look at that across. Now all of a sudden I have pre-existing groups that aren't randomized, that are probably going to be different sample sizes. Variability in my outcome could differ widely across these different groups. I start to lose the robustness of this and have to take a more conservative approach type of thing. But if we don't, this is a really nice way to go about things, okay? Basically what we're doing is we're running comparisons, but we're still using the overall design information from the overall design to run those comparisons. Kind of see what's going on with that.
I do have a quick question
Yeah.
on the formula. So you're saying the mean squared error is like relative to like the pooled variance between all groups. So why are there two, like when we're calculating it, if it's supposed to be relative to the pooled variance in between all groups, like why do we have two mean standard errors?
Yeah, because remember that whenever we're doing a pairwise test, we have variability, or we have error in this group and error in that group. Same thing when we're calculating your pooled or test statistic for independent sample t-test. It's the same formula. It's just instead of mean squared error, it's just pooled variance.
Oh.
So you still have, it's the same formula. You're just plugging in mean squared error. You're just plugging in a different variance estimate. It's actually the same variance estimate. It's just pooled across all of your groups as opposed to just the two that you're looking at.
And is there a calculation for that somewhere?
This,
Yeah, the mean squared error.
yep, that was all in sort of when we were cranking out ANOVAs by hand, remember last week? That's where that is.
That's what that is, okay.
Easier way to do that is just pull that out of your ANOVA table.
Okay.
Because it's right there. So. Other questions? All right, so planning comparisons, independent sample t-test, defensive approach. If I have just a couple of a priori comparisons and I just got a lot of people, I'm not too worried about stuff. Or if I have potential violations, what I can just do is I can just go through and in SPSS, I just run my independent sample t-test. I put in, like in this case, I have my ethnicity variable and drop that in, and I say I want to compare groups 0 and 1. I want a group 1 and 2 comparison on 1 and 3, so whatever. Just going through, easy, simple way to go through and do this. What we're doing with this, this is going to be a more robust sort of follow-up test. But what we're leaving on the table is sort of the additional power of if we don't have violations, if we run a nice tight experiment where we don't have violations, we're seeding power, but we're taking more robust approach. So really need to go through and think about like what's going on in my design when I'm going through and planning my approach here. All right. Linear contrast. Does anybody remember linear contrast? Did anybody have exposure to linear contrasts in prior methods, classes, anything like that? Okay. The thing with contrast, get this in sort of just to start out, linear contrast, it just breaks, it's still just an independent sample t-test. That's all it is. It just breaks down to a t-test. What we're doing though is we're incorporating multiple groups with our contrasts, okay? So what we can do any linear contrast, the t-test is a linear contrast. But when we talk about linear contrast within the context of traditional methodological designs, generally what we're talking about is a comparison between a set of means. It can just be two means, but what we can do is we can start to harness our equations to go through and start to look at comparisons across groups of people, as opposed to just this group versus that group. This allows us to get pretty flexible in testing our a priori hypotheses. And again, all this is just a generalization of the t-test. We're gonna go through some math that's gonna seem kind of scary maybe, but just keep remembering in your mind, at the end of the day, it's just a t-test is all it is, okay? So what we're doing with our linear contrast is what we need to do is we have to specify a linear combination of means, okay? And so in this situation here, this a sub 1, this is just a weight. This is just some weight value that we assign to mean 1, mean 2, mean 3, so on and so forth, however many means we have, right? And we can sort of talk about it until we can note this quickly, just as the sum of the weight of A sub j times the mean of group sub j, okay? So let's say, so basically we're just have a linear combination of a weighted sum of the means, okay? If I were to say, set my weight for all of these means equal to 1, I would just have my linear contrast would just be the sum of all my means, right? So if I take 1 times the mean of group A plus 1 times the mean of group B plus 1 times the mean of group C. If I set all these weights is equal to 1, my linear function is just going to be a sum of my individual weights or sum of my individual means, okay? But if I go through and I set all of my weights to be equal to 1 divided by the number of groups in my design, now all of a sudden I've got the mean of all groups. So let's say I've got 3 groups, right? And I go through, so I assign the weight to each one of those groups to be 1/3. Now I've got 1/3 times mean A times 1/3 times mean B plus 1/3 times mean C. Essentially what I've done is I've just taken the average across all groups. So all we're doing with this is we're just assigning weights to our means to start to give us certain types of combinations. Okay. If I'm talking about a linear contrast, we identify this as this psi symbol, okay? A linear contrast is defined by a combination that's restricted so that the sum of my weights is going to be equal to 0, okay? So if I have 3 means here, and I assign the weight for mean 1 to be 1, the weight for mean 2 to be -1, and the weight of mean 3 to be 0, if I go through and I add 1 plus -1 plus 0, the sum of my weights equals 0, which means I have a linear contrast, okay? And so if I would write that out, the value of my contrast would be my weight times mean 1, right, plus my weight times mean 2, plus my third weight times mean 3, okay? What have I essentially done here? Allison?
You're just like subtracting mean 2 from mean 1.
Yeah, I just basically have the difference between mean 1 and mean 2. 0 with this weight drops out mean 3 out of the equation. Mean 3 is gone, group 3 is out of the picture. And essentially what I've done is I've just specified a contrast comparing group 1 and group 2 from one another. Okay. People see how that worked out? Okay. What if, let's say I set weight for mean 1 for group 1 to be 1/2, weight for mean 2 to be 1/2, weight for mean 3 to be -1. If I add 1/2 plus 1/2 plus -1, again, get 0, I've got a linear contrast, okay? I go through, weight these, what have I got here? Awesome.
You're averaging 1 and 2 and then subtracting 3 from that.
Yeah, what I've got is, and this is my classic contrast, right? What I've got is in my head, what I've hypothesized is I'm saying I believe, so I've got three levels of three different groups in my ANOVA, right? But what I'm saying is, I'm saying the combination of groups 1 and 2 is gonna be larger than whatever the mean of group 3 is, right? So let's say I've got experimental condition 1, experimental condition 2, and then control group. And my hypothesis might be that my 2 experimental groups are gonna outperform my control group, okay? Or if you're a clinical person, let's say I've got active treatment 1, active treatment 2, and then some just kind of waitlist control. My hypothesis here is that my symptom levels are going to be, I might switch this around, make this -1/2, -1/2, and +1. And what that would so correspond to, I'm guessing that symptoms are gonna be slower in the combination of my 2 active groups relative to my waitlist control group, okay? So all we're doing when we're setting up our weights is just making these consistent with whatever hypotheses I've developed for this thing. And what I can start to do with these linear contrasts is I can start to test very specific comparisons that involve multiple groups as opposed to being limited to 1 versus 2, 1 versus 3, 2 versus 3, that type of thing, right? I get more efficient in this way. Yeah.
Is it fair to assume that the group that is 0 or -1 is a control group?
No. That's it. So it's just based on the comparison, sort of based on how you set that up,
Oh.
okay? And we'll go through and we'll work through this. Yeah, Gabe?
I finally remember I did something like this a long time ago, but you can use whatever numbers you want as long as it's
Yeah.
not 0, right?
Yeah, you can. And we'll talk about where that starts to become relevant. Yeah. Yeah, the weights are completely arbitrary. You can use whatever you want to. For the statistical test, you could have this be 5 million, 5 million, and negative 10 million, right? Like, it's gonna give you this, you're gonna have a lot of zeros in there, but like, that's completely arbitrary. But when we start to get into effect size stuff, it starts to make a difference, so. All right, so how do I select my coefficients, right? Actually, pretty simple, okay? First, what I wanna do is I wanna identify the set of treatments or groups to be compared, okay? Of my set of groups that I have in my design, which ones do I wanna compare? Then what I do is I assign weights as the reciprocal of the number of treatments in that set. So however many groups are in set 1, however many groups are in set 2, I just take that number, 1 over that, those are my weights, and then just assign negative coefficients to one of those groups. Typically, it's gonna be the group that you think is gonna score lower than the other group, okay? So let's say I've got a pretty big one-way ANOVA where I've got 5 different conditions in here. And what I wanna do is I wanna look at the difference between the combination of 1 and 2 versus the combination of 3, 4, and 5, okay? So what I would do is I would say, okay, here are my means, right? So I've got a set of 2 and a set of 3 that I wanna compare. So what I'm gonna do is I'm gonna assign weights as the reciprocal of the number of groups in that set. I've got 2, so I got 1/2 and 1/2. 3 here, 1/3, 1/3, 1/3. And then what I need to do is assign one of these groups to be negative. So I'm gonna make these my 1/3 negative. With this game, what group am I expecting to sort of score? What group am I expecting to score higher on than which group?
Sorry.
Which group am I expecting to score higher here, based on if my hypotheses are consistent with how I've assigned my weights?
Should it be like the first 2?
Yeah, my first 2, I'm expecting these first 2 to score higher, because if, what I'm gonna do then is I'm gonna take the combination of these 2 minus this other one, and if these score higher, then it's gonna be sort of positive. I don't need to, I can assign negative weights to these and positive weights to these, it's just the value of my contrast is gonna be opposite of what's actually going on in the set, so you just need to be careful and think about that. But if you take this approach, the value of your contrast will make conceptual sense in terms of direction. So just be aware of that. But if I go through and I take 1/2 plus 1/2 plus 1/3 plus 1/3 plus 1/3, I get the sum of my weights equal to 0. I know I have a linear contrast. Okay. So value of my contrast is going to be the sum of my weighted means, right? So I've got 1/2 times x1 plus x2 minus 1/3 times x3, x4, x5. So And so this is just gonna be the amount of value of my contrast. Now, if I have linear coefficients with absolute values that sum to 2, this is where I have what's called a standard set, okay? So Gabe, yes, I could set this up, I could have this be, I could make this -2, -2, -2, and that be +3, +3, right? 3 + 3 - 2 - 2 - 2 still equals 0. I've got a linear contrast, right? But what happens is if I want to go through and use the value of that contrast to calculate my effect size, which is kind of a nice thing to do, what I need to do is I need to have a standard set. And so if the sum of the absolute values of my weights is equal to 2, then I have a standard set. So if I take 1/2 + 1/2 + 1/3 + 1/3 + 1/3, that gives me 2, and I know what I've specified is a standard set. Okay, where this starts to come into play into the difference between SPSS and Stata. If I've got 1/3 as a weight, and I punch in 0.33, SPSS will only let me go like 3 decimals. So if I add plus 0.33, 0.333 plus 0.333 plus 0.333, do I get 1? No, I'm just a little bit off, and so it futzes with it a little bit and lets it not. So I don't end up with an actual linear contrast. It's a little bit off, right? Stata, if you go through and set it, Johnny, specify, I think like 6 decimals, it just treats it as a repeating, and we'll go through and do it. But if I wanted to get an exact test in SPSS, which we'll need to be aware of at some point, what I would need to do is I would maybe need to switch this over. If I want to get an exact p-value, I would need to turn that 33222 so that I get whole numbers in there, so it'll actually calculate a linear contrast. Because if I don't, it's going to be close, but it's not going to be perfect. And so what's going to happen is my p-value is going to be a little bit off. My test statistic is going to be a little bit off.
Then you don't have a standard set.
Then I don't have a standard set, and that's fine. What I would just need to do is then go through and probably do some hand calculations to get my effect size, proper effect size estimate. All right, so this is all well and good, but if I have dramatically different cell sizes, it starts to degrade my confidence in what's going on. So again, all of this whole procedure is based around the idea of sort of nice, tight experimental research. If I start to have weird violations, then it starts to throw me off with some stuff. So just something to keep in mind. So, classic test for my linear contrast, okay? What we would get and calculate from a classic approach, calculate a sum of squares for my linear contrast as a function of my treatment means and my weights, okay? So here side, this is my linear contrast. This is just what we did in the last slide, okay? If I'm gonna go through and use these to calculate my test from a classic approach, what I would do is I would calculate a value for my sum of squares contrast that's gonna be equal to the size of my cells times the square of the value of my contrast over the sum of my squared weights. Okay. If I have unequal cell sizes, they're not the same number of people in each. I just modify this formula to take the square of the value of my contrast over the sum of square of my weight over the sample size there. So let's say I've got 3 different means, X1, X2, X3, 10 people each group, and I assign my weights to be 1/2, 1/2, and -1, right? Daniela, what does this set of weights give me a comparison of?
0.
Yeah, if I add them up, but
Yeah.
conceptually, what's the comparison of the groups that I'm testing here?
You are. What do you mean, like with the X's over there?
No, with these weights, if I assign these weights, what are the groups, what combination of groups am I testing here?
I'm confused, like 1, 2, and 3. Like, I don't know what you're looking for.
Yeah, so 1, 2, and 3, Johnny, you know about?
It would be 1, let me make sure I say this right. The contrast of interest is 1 and 2, and then 3.
Versus 3, yeah.
Oh, because it's 1/2 left.
Yeah.
Oh,
So,
okay.
so the weights here, right? So if I look at these weights, I can infer that what I've got is what I'm setting up here is the comparison of 1 and 2 versus 3.
I see.
Okay. So if I go through and I take, if I go through and add these up, I get 0. That tells me I have a linear contrast and also a standard set, because if I go through and add the absolute values, I get to 2. But conceptually, what I'm doing with this set of weights is I'm comparing the combination of groups 1 and group 2 with group 3 in this.
Okay.
Okay. So here, what I would do, value my contrast, give me 1/2 times 1.5 plus 1/2 times 2 plus -1 times 3 gives me the value of my contrast as -1.25. Okay. Now, the nice thing about this is if I have a standard set, this is very literally the difference between the average of my first 2 groups and compared with my third group. Okay. If I go through and I assign different weights to this, if I assign, let's say 5, 5 and -10, I can do that. But the value of the contrast I get isn't sort of the difference in those means and sort of the actual scale that I'm using. And so that's where things start to get a little bit tricky. Okay. You see that, Gabe? With the, okay. So this is where you can use whatever values you want. It just makes it easier if you can set up something that turns into a standard set, because now the value of my contrast is very literally the difference between the groups that I'm comparing. Okay. In whatever metric that I'm using in terms of my scale. So the sum of squares contrast here is going to be the number of people in my sample in each one of my cells is 10 times the square of my the value of my contrast here, -1.25 squared over the sum of my squared weights. So I've got the sum of 1/2 squared plus 1/2 squared plus -1 squared. If I go through and run that out, that's going to give me the my sum of squares contrast. Okay. And because my linear contrast give me a 1 degree of freedom test, I know that my sum of squares contrast is going to be equal to my mean squared, right? To get mean squared, I take my sum of squares divided by my degree of freedom. My degree of freedom 1 is 1, then my sum of squares is equal to my mean squared, right? And so because of this, what I can do is I can take my mean squared contrast divided by the mean squared error from my ANOVA table. It's going to give me an F statistic. F statistic is going to be my mean squared contrast over my mean squared error. And what I do is I test that against my critical value of F with 1 degree of freedom in the numerator and what are the degrees of freedom error for my ANOVA are there. Okay. So this is the classic approach. This is your sort of classic approach to going through and calculating your test statistic for these contrasts. Okay. And this is a nice and fine way to go through and do things. But the way SPSS will do this, the way Stata will do this, is going to do it in a way that it's mathematically equivalent, but it's just going to give us some values that are a little bit more helpful in doing things like calculating confidence bounds and things along those lines. What SPSS is going to do is it's going to calculate your T statistic that you get for your contrast as the value of your contrast over the standard error of your contrast. Standard error of your contrast is going to get calculated as your mean squared error times the sum of your squared weights over the number of over the individual cell sizes. Okay. And then your T critical, again, just like it was before when we were looking at the paired comparisons, it's just going to be a critical T for a two-tailed test with degrees of freedom equal to degrees of freedom error from your overall ANOVA table. Okay. So again, if I have a balanced design, my classic F and my SPSS T is either functionally equivalent. There's differences that come up if I have unbalanced. And if that unbalance starts to get quite large, that's where we start to worry about the validity of some of this stuff. But what we get here is a T test that makes a little bit more sense for those pairwise comparisons just in our brain because we're used to seeing that as T. We also get a standard error estimate that we can use to calculate confidence bounds and things like that. So this is kind of a nice way to go. So when you're doing hand calculations, use this approach, right? Don't go classic F. I mean, you can if you want to, it's just going to be more steps and things like that. This is going to be a more efficient way to go through and do the types of things we want you to do, okay? But SPSS does it. It also gives us corrected tests and standard errors for violations of homogeneity of variance, right? So when we go through and we request our and request contrast within SPSS. SPSS, just like it does with t-test, it's gonna be equal variance is assumed, equal variance is not assumed. And at one point I was able to pull the formula for how it's going through and doing that, just because I wanted to know exactly how it's doing that. I've been able to identify no empirical validation, but I don't know where IBM got this from. And this link that I used to have that sort of showed like documentation for this is no longer available on the interwebs, so I don't know, right? But again, like we'll go through and use these, but it's just also thinking about like, so like, what's going on? I mean, I don't know, because this is the thing, like, we can't just trust SPSS to do the right thing, because there's plenty of stuff in that package that you beg, okay, it's gonna give you this, but this is calculated wrong in this, so you ignore this, right? That happens. Starts to become particularly relevant for R programs. Who uses R? Johnny uses R, Gabe uses R a little bit, right? So this is one of those things, it's a great community, but just because someone wrote it and you can download it in R doesn't necessarily mean it's right, right? So I just wanted to be careful and sort of cognizant that you know kind of where your numbers are coming from. Okay. So if we're thinking about managing our family-wise error here, okay, what we typically do is we look at plan contrast at per comparison error rates, okay? But depending on how many actual contrasts I want to run, let's say I have like literally 5 different contrasts that I want to take a look at. Boy, that's still sort of quite a few tests, even if I predicted it on the front end, right? So some solutions to think about with this. One, against reduce the number of contrasts. Again, like, do you really have 5 critical comparisons that you need to have in order to answer your question? If you do, fine, but if you don't, sort of thinking about managing the number of like predictions that you're making. Other thing you can do is you can sort of just assume a more stringent alpha level to start to correct for this stuff. Yeah.
Phone keeps buzzing a lot.
Oh, is it?
I don't know if there's an alarm going off or.
No, probably a text group where everybody's
Oh,
apparently no one
I
works, right? Like, I don't know. I guess no one else has jobs and has just all day doing this screw around text each other
Like,
back.
I thought it was great.
Oh, sorry.
I still
Control your phone.
Just gonna send a text out to my entire contact group, like, hey.
2 to 5 on Wednesday. All right.
All right, so some ways we can go about doing this. We can have a Bonferroni test, okay? This is your correction to your family-wise error. What we're just doing here, people keep leaving. This is important. Bonferroni test is like incredibly simple. Don't try and make this harder than it needs to be. Bonferroni test, all we're doing is we're adjusting our alpha level, okay? We're just setting a new alpha level, a new level for our p-value. And so where that's going, okay? So what I want to do, Bonferroni, so easy. This is why everybody Bonferroni corrects for every goddamn thing, and it's not appropriate to do. Bonferroni should be used for tight comparison of a set of a group of planned tests, okay? Bonferroni is not a post hoc correction, okay? Because it's incredibly stringent and you're gonna overcorrect for things with this. All we're doing with Bonferroni inequality or a Bonferroni correction is we're gonna take our alpha, which is almost always gonna be 0.05, and we're just gonna divide that by the number of tests that we're planning to run, okay? So if I've got a probability of type 1 error is 0.05, and I have 3 comparisons, all I'm gonna do is I'm gonna take 0.05 divided by 3. Someone do that. What's 0.05 divided by 3?
0.01666.
0.017, call it, okay? If you are gonna run a Bonferroni correction for 3 tests, and so you take that and you get, oh, my alpha prime, my Bonferroni alpha is 0.017. Money beats, that's all you got, that's all you need to do. Then you just run your tests And anything that has a p-value of less than 0.017, you get to claim evidence for that. If it's above 0.017, then you say, well, we haven't met the threshold that we would need to conclude evidence for an effect. So if I get 0.03, it's not less than 0.017, and so I would say we don't have support for this test, fall in correction. If it's 0.001, we would say, yep, we have evidence with Bonferroni correction of support for this. What ends up happening is people try and get like, they think about it too much and then are started trying to get like a Bonferroni corrected critical T that, nope. It is, you're just calculating a new alpha and then you look at your p-value. Your p-value is less than that new alpha, then you have evidence for an effect. If you don't, you don't. That's all you gotta do with this, okay? Okay.
Two things. So it doesn't impact your t-value at all. then?
Nope, doesn't do anything to it.
And the other one is, so is the Bonferroni correction, is that essentially the opposite of this error rate per experiments that you're telling us about?
Yeah, this is what we're trying to do here is just adjust for family-wise error, right? And so what we're saying is because I know that if I were to go through and run each one of these tests at alpha 0.05, my probability of at least one type 1 error is about 0.15, right? So what I'm gonna do, or this would be actually the number of type 1 errors across these tests. Well, no, this is probability because this is the inequality. Probability can exceed 0.15. That's the most that you could have. So what we're gonna do then is for each individual test, we're gonna adjust my alpha. So no amount alpha is not 0.05, it's 0.017. And so across this set of comparisons, that's the new threshold that I have to get in order to reject the null hypothesis, okay? So Bonferroni is nice, it's easy, it's beautiful, because all you do is you just calculate a new alpha level. If your p-value is less than that, you're good. If it's not, you fail to reject. That's all you gotta do, okay? Same thing with confidence bound. Confidence bound is a different thing. If you calculate a 95% confidence bound, still calculate your 95% confidence bound because you specified it's a 95% confidence bound. If you don't want to, if you want a 97.5% confidence bound, calculate that. But this is my confidence bound. This is my my data supported estimates for upper and lower values of population parameter. This is just for making yes, no rejections. Okay.
Okay, so for Bonferroni, so if your Bonferroni value is less than the calculated p-value, then there is evidence for an effect.
No, if my Bonferroni is 0.017, and if that's less than my p-value, and my p-value is 0.04, then I don't fail to reject it. Basically, you're just shifting your alpha. You're choosing a new alpha level that's more stringent than 0.05. And that's just to try and control this family-wise error across the set of comparisons. Okay. Other tests, so again, Bonferroni appropriate with a small number of planned comparisons. If I just go through and look at all possible pairwise comparisons and I set on Bonferroni for that, SPSS will do it for you, but it's way too stringent. Like you're gonna make it far more difficult to identify the things that you want to identify. Because if I've got 7 different pairwise comparisons, now I've got alpha divided by 0.05 divided by 7. Just gonna start to get like a really small value. That's an exceedingly high, it's too much. So do not use this for post hoc comparisons, right? This is to be used to correct for family-wise error or a set of planned comparisons. I'm just being conservative in my approach because for whatever reason, I just really want to make sure that I'm not making type 1 errors. Yeah.
And SPSS is too stringent and we want to run this test. Should we use a different software or just use it for like the familial?
No, you just need to know what to ask your software for, right?
Okay.
Software, like any other software, it's just gonna do what you ask it to do. If you ask it to do something that's ill-advised, it'll do it for you, but it might not tell you that it's ill-advised. So it's just up to you to think about like, how am I gonna go through and approach this? Okay. Other correction that we have here that gives a little bit more precise control is gonna be our Dunn-Sidak test. Okay, and again, the same thing, we're just calculating a new alpha level, new alpha prime. This time it's just gonna be 1 minus alpha times, or taking the power 1 divided by the number of comparisons. Okay, a little bit more precise control, but it's gonna be very similar to your Bonferroni correction. Okay, so I use this if I'm wanting to feel fancy, right? It's a done sit. It's a little bit more, but the same thing, all we're doing is we're calculating a new alpha value. In order to claim evidence for an effect, we just have to have our p-value fall below that, okay? We're not doing anything with t, we're not doing anything with confidence bounds, we're just making an adjustment on the alpha for that test. Okay. Comfortable with this? All right. Confidence bounds and effect sizes. Confidence intervals for my contrast. SPSS calculates these for us now. It didn't used to, which is very nice of SPSS to get on board. I've just been trolling SPSS for years, and so it's really, so the power of my YouTube presence so really was driving so the big wigs at IBM. Confidence bounds, the same thing as we always go through and do, right? It's the difference between your two means if you're running a pairwise comparison times your critical T times the standard error estimate. Standard error estimate here is the same one we used to sort of run our hypothesis test. Okay? This is why, again, relative to the traditional F test that we can calculate for contrast, this is why just calculating a standard error is nice, because then I can just drop that in and then use that for my confidence bound. Alternatively, I can take the value of my contrast if I'm comparing multiple groups, right? Then it's just the value of my contrast plus or minus my critical T times my standard error. Okay. And again, making sure that critical T is based on the degrees of freedom error for my overall ANOVA table, right? Because we're still kind of working in that field. Okay. My effect size, again, effect size is going to look exactly like all of our effect sizes always do. It's either the difference between two means if I have a comparison, or the value of my contrast. Again, Gabe, assuming that I have a standard set and haven't used a bunch of wild numbers there, right? Then the value of my contrast is very literally the literal difference in sort of my groups that I'm comparing. Here we can use our pooled standard deviation. Here with the value of my contrast, a couple of different ways I can go through and use this as my standardizer. If I have a really nice design with relatively sort of balanced number of people in each one of my conditions, I haven't violated homogeneity of variance. Just the square root of my mean squared error for my overall ANOVA table. That's pretty clutch, right? Because again, the mean squared error in my ANOVA table is just the pooled variance across all of my cells, right? And so I can just use that if I've got a nice clean design. Just go through, find your mean squared error, take the square root of that. Johnny and Stata in your ANOVA table have a sort of at the top of it, it'll say have a value that's root MSE. That's just the square root of your mean squared error, right? Just go through and use that to calculate your effect size. Really nice. We could also go through, if I'm worried about homogeneity of variance, what I could do is I could use just the square root of the average variances in question, right? So let's say I've got 5 groups and I want to compare group 1 and 2 versus group 5, right? If I've got concerns about homogeneity of variance, so I got 3 and 4 aren't in my comparison, but they've got like maybe really big or really small variances or something like that, to where I'm not trusting my mean squared error to be really relevant to the groups that I'm comparing. What I can just do is I can take the average of the variances of the groups that I'm looking at, take the square root of that. That's an option. If I have unequal samples and the violations of homogeneity of variance, then what I can do is just take my the square root of the pooled variance from the samples in question, right? Here, what I'm doing is just going to go through and hijack my pooled variance formula, right? Pooled variance, right? We've got n-1 times variance 1 plus n2 minus 1 variance 2 right? Got that. But if I've got more groups, I just keep adding on to that, right? So now we got plus n3 minus 1 times variance 3, so on and so forth, right? And then I just go through and say, okay, well, now I've got N1 plus N2 plus N3. Minus however many I've got in there, right? We're just adapting that, so just getting the pool variance for the whole thing. Okay. So, now the only thing is I got a asterisk here. If I got really severe problems with unequals, violations of homogeneity variance and unequal cells, now all of a sudden my sort of contrast procedure starts to break down, and I might sort of be worried about inferences drawn from this. You'll want to keep that in mind, but if it's within reason, we can go through and start doing some of that stuff, okay? Or standard deviation of my control group also. So always, if I've got some reference group, I can go through and drop that in there. Right? So again, lots of different options, but it just requires you to think about what's going on with my data. What did I find on my screen? What am I seeing? And which one of these is going to be the best option for me as I'm moving forward with my calculations. And again, making sure if I'm gonna just drop in the value of my contrast as my numerator or my effect size, or for my confidence bound, I just need to make sure that my coefficients form a standard set. Okay. So here, some of the absolute value of my weights equal to, so I know I've got a standard set. Here, the absolute values of my weights don't equal to. These are equivalent in terms of my t-test or my actual hypotheses test, but it's not gonna make, so with this set of weights, the value of my contrast isn't gonna represent the actual difference between the groups. It's gonna be something larger. So just making sure that we're aware of that. Okay. Want to run through this in SPSS, kind of see what this looks like? Cool. Like the enthusiasm. All right. So what we're going to do is kind of build off the example that so we started out with. And so we're saying, given evidence of greater responsivities to similar versus dissimilar targets, what we're interested in is looking at the extent to which individuals from different backgrounds vary in their response to primes with homogeneous actors. So same type of thing, right? But what we're doing now is we've got a pilot sample of undergraduates who, and we group people in those identifying as white non-Hispanic, black non-Hispanic, white Hispanic, and Asian Pacific Islander, right? So we've gone through and said, okay, we've got some groups of individuals who are identifying with different backgrounds. And what we want them to do is we want to ask them to give ratings of subjective amusement. Again, not at all, most in my life, to a humor eliciting film featuring white non-Hispanic actors, right? So our hypothesis is like, okay, maybe we're going to go through and we're going to get different responding from people of similar backgrounds as sort of the target people in the film relative to people from different backgrounds, right? So maybe it's not the same thing for everybody. Maybe we're getting systematically different responses, right? And so what we've done, and these aren't sort of based on anything, this is more just for me to sort of give some examples, but let's say we expect that white participants are going to be more responsive to the film than non-white participants. Okay, so here we're using Census Bureau's the definitions of race ethnicity. So what we're looking, our argument is that our white non-Hispanic and white Hispanic groups maybe respond differently from my other two groups. Okay, then maybe my second hypothesis is my white Hispanic and my white non-Hispanic participants will be more responsive than black non-Hispanic participants. Right, so now all of a sudden I've got four groups, but I'm only gonna look at three in this contrast, right? And then black non-Hispanic participants will be less responsive than participants identifying as white Hispanic or Asian Pacific Islanders. Here we've got our white non-Hispanic folks, throwing those folks out, and we're just looking at our other groups here, right? There's no rhyme or reason. I mean, this is an interesting question from sort of a method diversity standpoint. These don't make any sense necessarily, but just to go through and sort of how do we go through and set up some different contrasts, okay? So let's go through and open up your one-way ANOVA planned or sort of one-way ANOVA planned contrasts. All right. Okay. So here we've got a much smaller set of individuals, right? We're not gonna worry about screening these folks just because we wanted to move forward to the good stuff here. But let's go through and pull your plan contrast worksheet. Okay. And what I'm gonna do is I'm just gonna go through, I'm gonna go analyze, compare means, one-way ANOVA, right? And so I got my background factor here, amusement's my outcome. We go through and we go options, descriptives, homogeneity, variance test, Welch test. We'll do means plot here, okay, continue, and then go ahead and hit paste. So here's my ANOVA statement. So I'm gonna go through, run my overall ANOVA. And pull up our output here just so I can kind of magnify it up, right? Okay. So just looking at our descriptives here. Mesa, what are we seeing up in this data set? Just based on our descriptives.
Means are pretty similar, same sample size for each group.
Yeah, so really good, right? So we're not going through the whole sort of skew kurtosis things along those lines. What's kind of the biggest thing, if you're looking at this, just looking at this descriptives table, what might be the biggest thing that gives you pause in terms of moving forward with this analysis?
Making sure that my min and max makes sense.
What's that now?
Looking at my minimum, maximum, making sure they make sense.
Okay, making sure it says, from a methodological standpoint, like how many people do we have in each one of these cells?
6.
Yeah, so there's not a lot of people in here, right? So like, this is gonna be an incredibly underpowered, like we're gonna be pretty limited in terms of what we can really infer from this, but we're saying that this is just a pilot, right? So they're gonna go through it to see, like just with a small sample, do we get people kind of responding the same way-ish, right? So we go through and make a note of that. But if we go down through and take a look, Kate, do we have problems with homogeneity of variance? Probably not. I don't know. Other thing too, remember that we only have 6 people per cell. And so the fact that I don't get a large P or a small P value on a horribly underpowered test doesn't tell me a whole lot about much, but at least not anything that's big enough that we would go through. So yeah, like we don't have sort of evidence for massive differences here, but sort of again taking everything in context, understanding how our tests work. Okay, Johnny, if I go down and take a look at my ANOVA, what am I finding? What can I might infer from that?
You'd below your 0.05 level.
Right, so I have evidence for a difference in there somewhere, right? So even with only 6 people in each individual, I'm still getting enough that is saying that, yeah, I guess maybe there are sort of differences in how different participants who identified from different groups are responding to this film. So yeah, I guess there's maybe something going on in there somewhere, huh? So might be worth pursuing it and going through and taking a look. And if I look at my effect sizes here, again, these are small, they're not super precise, but I'm saying in these data, about 43% of the total variability and amusement ratings can be attributable to participant background. That's pretty massive, right? My population estimate would be about 0.3, right? Or 0.33. Now, I don't know what SPSS is doing here. Can I have negative values for, yeah, so that should be 0. Your lower bound is always gonna be 0. You can't have negative values for that because it is nonsensical, but pretty wide sort of range of stuff. But it's saying, hey, maybe this is just a pilot. It's saying like, maybe we've got a signal in there somewhere, right? So what do we want to go through and do with this? Well, if I go through and I take a look at setting up my contrasts here, right? I've got we're pretending that I have three specific hypotheses about sort of how these differences might actually play out. So I'm gonna say, I guess with this we've set up, white participants will be more responsive than non-white participants. I guess we're sort of rolling sort of things together. We're sort of saying sort of minority groups as sort of relative to our white majority folks. We're gonna have a difference there, right? So in terms of setting up my contrasts, right? If I've got and this starts to become important in SPSS, knowing who your groups are and where they're located and how they're coded starts to become very important. Otherwise, you're gonna get everything scrambled around, right? So I have white, non-Hispanic, black, non-Hispanic, Hispanic, okay. So these are my groups, and I don't know to say 0, 1, 2, 3, okay. Along those lines. So what I need to do is I need to tell SPSS, I need to tell it what the values of my contrasts are gonna be, okay? Yeah.
How do we know they're in that order? I mean, I see them there, but this is after
Yeah.
running it, so.
Yeah. I mean, if you just go to your data set. Put your variable,
Gotcha.
got it in there, right? So just make sure that you know that, because that order starts to become important. So first contrast is I want to compare my white non-Hispanic folks to everybody else, right? So what I'm going to do is I'm going to say, okay, what are my groups to be compared? I've got one in this first group, I guess just to make this just so it's not that it makes a difference, but this is okay. So I've got one in my first group, so the reciprocal of 1 is 1, and I've got 3 in my other groups, so my weights are going to be 1/3. And then what I'm saying is I'm saying that my white non-Hispanic participants are going to be more responsive than all other groups, right? So who gets the negative on this?
Wait, can you repeat the question? I'm not apologize.
Yeah, so I've got my weights, right? And I know they're gonna be 1, 1/3, 1/3.
So it should be white, I mean, positive white, and everything else is negative.
Yeah, because my hypothesis is that these three groups, the combination of these groups is gonna score lower. And so I'd assign the negative to those groups, just so that the value of my contrast makes some sense in terms of sort of direction, okay? And then I'm gonna say my white Hispanic and my white non-Hispanic participants will be more responsive than my black non-Hispanic participants. Okay, how many groups am I including in this contrast? Olivia?
3.
3, right? Who are the odd folks out here?
Asian Pacific.
My Asian Pacific Island folks, so they're out 0, right? Now, how many people in my 2 groups? So I've got saying my white Hispanic and my white non-Hispanics, right? That's gonna be what are my weights gonna be for those 2 groups?
1, sorry. 1/2?
1/2.
1/2, 1/2, 1.
1/2, 1/2, and 1. And who gets which weights gets the negative here?
Black, non-Hispanic.
Right. So we're saying our hypothesis is that like, okay, so there's sort of white non-Hispanic characters, but maybe the combination of these folks are going to be sort of even more responsive than participants who identify as black. Okay, and then black participants will be less responsive than Hispanic or Asian participants. So here I'm going to say again comparing my black non-Hispanic folks to the combination of Hispanic and Asian folks. So again, 1/2, 1/2, right? Again, expecting my black respondents to be less responsive to sort of the maybe this just sort of for sort of matching purposes, right? And so then white non-Hispanic folks, you guys got kicked out of that one because you're not relevant to that comparison. Okay. People see how we set up these weights and why these make some sense, sort of, and how we can start to manipulate these to start to look at the comparisons that are interesting to us and are consistent with whatever hypotheses that we're running. Okay. So what I'm going to do then is I'm going to go back into SPSS. I'm going to go to analyze. I'm going to go to compare means, one-way ANOVA, and everything's kind of set up in here. But this time what I'm going to do is I'm going to go to contrasts. Okay. And I'm going to start entering my contrast. So my coefficient for this first set is going to be 1, add, and then it's going to be what?
Negative 0.33.
The 3, and it just gives me 2 decimals, and then it's not saying anything else, right? So I'm going to say, okay, and then you got negative 0.33.
Well, like 0.01 left over.
Yeah. Okay, so that's my first contrast. Okay, say next, what's my first coefficient?
0.5.
0.5. Next,
Negative 1.
negative 1,
0.5
0.5,
and 0.
and okay. So you can see this is fairly tedious. I'm going to jump forward. I'm going to hit estimate effect sizes for contrast. Then you go through and take a look at sort of see what I want to use as my standardizer. Use pooled standard deviation for all groups as the standardizer. That's going to be the square root of my mean squared error. Or use pooled standard deviation for those groups involved in contrast to the standardizer. I didn't have violations of homogeneity variance, so I might as well capitalize on to the maximum set number of people. So I'm going to leave that there. So I'm going to hit continue here, and I'm going to go through and paste. Now I'm missing one of my contrasts, but I also don't really like sort of screwing around with SPSS's interface here. So what I can do is I can just go through and copy this out. And then just tell me what the values are for that last setup.
0, negative 1, 5, 5.
There we go. Okay. So just an easy way to go through and do it as opposed to sort of working through kind of that bulky system there. All right. So what I'm going to do is I'm going to go through and run this. It's going to give me my contrasts here. And so if I go through, first thing it's going to give me is my my table of contrast coefficients. Always take a look at this and make sure that the groups that you have specified are actually the groups that you wanted to specify. Make sure that all this matches up, right? So here I've got a group of my white non-Hispanic participants versus everybody else. Here are my white Hispanic and white non-Hispanic and Hispanic groups versus my black non-Hispanics. And then black non-Hispanic compared against Hispanic and Asian groups. Okay, this is consistent with what I wanted to do here. Okay, then we go down through, and we've got basically what is functionally the same thing as our t-tests, right? We have equal variance is assumed, equal variance is not assumed. Do we have violations of homogeneity variance that we noticed? No. So we're going to go ahead and start to interpret this top row. Here we have a value of our contrast, right? Here we have standard error for our T's, our test statistic, degrees of freedom, p-values, and then confidence bounds around my value of my contrast. Okay. Now you note that this has a subscript here or superscript. Some of the coefficients is not equal to 0 because I would only let me give 0.33. What that means is that this is not technically a standard set. which means that this T value is not exactly right. The value of my contrast is not exactly right. If I were to go through and actually run this out with these means by hand, I think the value is actually negative 0.5. Okay. So be aware, I can go through, and what I can do is if I go through and I set weights for this first one to be 3, -1, -1, -1. Now it's gonna give me a precise T statistic, which is good. But the value of my contrast is gonna be off in terms of it's just not gonna represent sort of an actual, the actual difference in those means, right? So this is fantastic, but just recognize that sort of it's gonna have some limitations in terms of stuff that you're doing. Johnny was stated if you go through, if you hit sort of decimals to I think like 6 places, it's just automatically gonna do it and it'll fix that. But SPSS doesn't have the capacity to do that necessarily. Okay. So if I go through and take a look, it looks like I have evidence for hypothesis 2 and evidence for hypothesis 3, right? Which is good, but not evidence for so my first one. Even though this is off, it's not gonna be that much off. It's very clearly not even close, right? Evidence for my second 2 hypotheses, but not for my first. Okay. And then if I go down through and sort of look at the end, here we have our effect sizes. Okay. And again, I requested using the square root of the mean squared error as the pooled variance of all my groups as my standardizer. Here is my standardizer. Here's the point estimate of my effect size. And then here's the upper and lower bounds for that. But again, recognizing that because the value of my contrast is a little bit off because I have 0.1 difference there, then my effect size is gonna be a little bit off, right? So just recognizing that thing. And if you run into a situation where that's happening, probably gonna wanna go out and just crank that out by hand just to make sure that you have a precise estimate. Okay.
So
Yeah.
for our problem sets,
Uh-huh.
if that occurs, what do you want us to do?
I would probably calculate by hand. Or pair up with Johnny Walker, is in his stated program. We'll go through and do that. Okay, but no, calculating that out, it's easy. It's not hard to do it
Can we
through.
bug SPSS about this?
What's that?
Can we bug SPSS?
Yeah,
about
it'll
this?
take it another 10 years or 8 years to go through and figure it out before they catch up to where I'm at.
Simple, just give me a couple more. Yeah.
All right. All right. So just to finish up, right? So here's SPSS for our omnibus effects. Here, me just calculating out our effect sizes for this and our contrasts. Here's what we just got in our handout that we saw, right? Johnny, this is same thing, setting up individual contrasts here for you because SPS or Stata won't give you automatically calculate your effect sizes for these contrasts. But here, if I just hit DI, that's short for display, and then you're just calculating, I just copied and pasted that, and then sort of your for that root MSE, and then it just sort of gives you the same thing as what other people get there. Here, Kate is me running through and doing that sort of just by hand, right? So easy enough. Okay. And then here's our write up.
Short enough,
What's that?
nothing.
Well, but this is what happens, right? And so this is something to think about, like as our designs start to get bigger, like there's just more things to go through and account for and talk about and sort of come into play. And so this is where we had just 3 very specific hypotheses about how this stuff turns out. If I were to look at all possible comparisons across those groups, right? Yowza, right? So again, it starts to be thinking about like, as I'm developing my studies, like making sure that things are sort of reasonable. And I'm only looking at things that are sort of most important to me. So again, here we're saying results of the one-way ANOVA, moderate effect, evidence against the null hypothesis of equal response to emotionally eliciting stimuli. So my statistics based on these data, we say background of expecting to count for about 33% of total variability in amusement ratings in the hypothetical population viewing this film. Like if we were to take all people from these backgrounds and have them watch this film, what would we expect it to account for? There we go. See, support for specific operator comparisons were mixed, right? Observed scores in the study were generally inconclusive with respect to differences across amusement, white, non-Hispanic, and other combined minority groups. And we're not saying that we're not saying they're the same, just saying we failed to reject. So it's inconclusive in terms of stuff, right? Particularly inconclusive given we only had 6 people in each cell, okay? Comparisons did, however, provide moderate evidence for greater amusement, the combination of white, Hispanic, and white non-Hispanic versus black non-Hispanic respondents, right? So here we're just giving all our statistics here. Ratings of amusement combination of white, Hispanic, and white non-Hispanic groups, 1.3 standard deviations higher than our other groups. And here we're just giving estimates of like sort of what that actual point difference is, right? Same thing with theory, our next hypotheses here, same type of thing. Down to the bottom, kind of tying this all together, saying results suggesting that background may be an important consideration in selecting emotional primes based on stuff. Precision estimates of these data was small, given the limited number of participants in each group. Lower bound estimates for population differences in these groups were while modest, may hold practical significance given their limitation of sort of range. Like, I mean, 0.76 or about 1/4 of a point or 3/4 of a point. That's not a ton, but we've only got a 0 to 8 scale. Also recognizing that these our point estimates are pretty large in terms of the effect, right? We say results suggest continued research evaluating ethnic cultural differences and responsivity to standard emotional primes is needed to look at specific attention to mismatches between participant characteristics and characteristics of individuals presented in these films, right? So again, just trying to take a thoughtful response back. Okay, hey, we've got these stimuli that we call standardized stimuli that are sort of, hey, good for everybody, but are they getting the same response from everybody sort of based on some of this background matching types of things, right? So just trying to tie this together to say, just because like the absolute difference there isn't sort of on the lower bound, maybe isn't a huge amount. I don't know, systematically, if someone's sort of just that much less than they're like, so what's kind of going on, maybe thinking about like wanting to sort of take some of this into consideration and thinking about how we're designing our studies, stuff like that. So just kind of rolling that all together. Okay. How are we doing? Like, this is like exactly kind of where I was hoping that we would get to. So still have to talk about our post hoc test, but we can sort of finish that up. How are people feeling about this?
I'll tell you once we do the
need to
problem set.
process.
Okay.
Give us some time.
All right, we do have some time, so go through, what we'll do is next week, we'll go through, finish up the last of this. And then assign the problem set. What I will do is get this problem set out to you, sort of. I'll get it to you after Friday. I don't want you to have, if you're working on a problem set, I hate dumping another one on there for you to look at, so be worried about. So we'll go through, get that done, and you'll have lots of time to go through and work on this. Just get with your partner, work through it, get started earlier, because this is again gonna look more like problem set 4 than your other ones, just because you're actually gonna be working with data. Yeah.
I was wondering if you have an estimate for when that'll be due. I'm gonna be out of town for ABCT, and then, like, I know a lot of people are going out for Thanksgiving.
Yeah, so it'll probably be, so this one will be due like sort of Monday when we get back from Thanksgiving or something like that. So, yeah, so I don't know, coordinate with people, sort of go through and work on. The thing that I could push it farther back. The problem is that this last set with the factorial stuff is gonna be really sort of a lot. What I would prefer and not have you do is then have the last 2 weeks of class just be like nothing but ANOVA stuff. So plan appropriately, get started early, and sort of kind of figure out, talk with people. So the magic of Zoom allows people to sort of connect effortlessly throughout the world. So just go ahead and plan however that makes sense to you. Okay, awesome. Thanks, folks.
Are we giving new partners or is it a similar one, same one that's,
What's that?
or like this, the next problem, that we're getting new groups or are we using?
Oh, yeah.
Are we
For-
doing
for-
3? Are we doing 2?
Are people happy with 2? It seems like or are people indifferent? It seems like people are relatively indifferent.
Maybe 3, I don't know.
I don't know,
Cause it's a lot. It's gonna be a lot.
I think Thanksgiving, I feel like it's easier.
Yeah, probably would be easier. So I'll set up pairs. It'll make it easier for people to go through and get together, but we'll go through. I like, maybe it'll be different people or maybe random.org just like wants you all to be in the same pairs like forever.
Do you know when we'll have our board?
Yeah, like my goal was to get it to you today, but I got caught up with other things. I'll get it to you tomorrow. Friday. Awesome. Thanks, everyone.
Bye, Abby.
Bye.
Oh, bye, Abby. Yeah.
Bye.
Next year.